మ్యూట్ చూడండి. వచ్చిందా? Good evening, sir.
Yeah, good evening. Hope I'm audible.
Yeah, audible, sir.
Yeah. So hope you are able to see the slide. I am sharing the slide just for me.
Sir, good evening, sir.
Sir, good evening, sir.
Sir.
Sir, can you see the slide?
Yeah, we are seeing, sir.
So hope slides are changing.
Yeah, changing, sir.
Good evening, sir.
Good evening, Andy.
Sir, we'll start by 6 o'clock, sir.
Okay, sir. Okay. So how many are attending, sir?
Sir, total 316, sir. Out of that, I think they're joining around 250 to 275 expecting, sir.
That is very good number, sir.
Sir.
So getting those many participants.
Yeah, from around 185 colleges, they joined, sir.
Oh, very good.
Good evening, sir.
Good evening.
A warm welcome to day 5 of our FDP. We are excited to continue our enriching journey with all of you. I, Ms. B. Ramya, Assistant Professor, gives me immense pleasure to welcome you all to the day 5 session 1 of our ACTE ATAL Faculty Development Program on Sustainable Practices and Innovative Trends in Civil Engineering. We extend a warm welcome to all our resource persons and participants joining us today from various institutions across the country. We look forward to an engaging day ahead with esteemed speakers and insightful topics. We are privileged to have Professor C.N.V. Satyanarayan Reddy sir, Professor Andhra University, on geosynthetics in sustainable constructions. Before we begin, I now invite our faculty colleague, Ms. P. Sridevi ma'am, Assistant Professor, to formally introduce our eminent speaker to the audience. Over to you, ma'am.
Thank you, madam. Good evening, everyone. It gives me immense pleasure and honor to introduce our eminent guest and today's speaker, and also my Guru Garu, Dr. C.N.V. Satyanarayana Reddy Garu, is a professor and head Department of Civil Engineering, Andhra University, Visakhapatnam, and has 33 years of teaching, research, and consultancy experience. His expertise and research interests are in the areas of reinforced soils, ground improvement, landfills, soil retention in excavations, deep foundations, and forensic geotechnical engineering. He obtained B.Tech degree securing first rank from Nagarjuna University, M.Tech degree in geotechnical engineering from IIT Madras, ME structures from Andhra University, and PhD from NIT Warangal. He has guided 17 PhD scholars and 125 M.Tech dissertations so far. He has more than 130 publications and in various national and international journals and seminar or conference proceedings. He has organized 50 seminars, workshops, and training programs. He has successfully organized international workshop on scour and erosion and the prestigious Indian Geotechnical Conference 2020 during December 2020. He is a recipient of Engineer of the Year 2006 award from Government of Andhra Pradesh and the Institution of Engineers, AP State Center, Dr. Sarvepalli Radhakrishna, Best Academician Award 2014 from Andhra University, and AP Scientist Award 2020 in the discipline of Civil Engineering from Government of AP and AP State Council of Science and Technology, AP State Best University Engineering Teacher Award 2022 from Government of Andhra Pradesh on the occasion of Teachers Day. He has got 14 Indian patent publications and 1 Australian patent granted. He handled research projects funded by Department of Science and Technology, New Delhi, University Grants Commission, AICTE and RUSA. He is an established consultant to various local, state and central government engineering organizations. He is a reviewer for Indian Geotechnical Journal, the Institution of Engineers, Journal of Civil Engineering, ASCE Journal of Materials, International Journal of Payment Research, and Transportation and International Journal of Earth Sciences and Engineering. He is a Life Fellow of Indian Geotechnical Society, the Institution of Engineers, and is Life Member of Indian Roads Congress, Indian Concrete Institute, Indian Society for Technical Education. He is nominated IGS member in International Technical Committee TC 213 on Scour and Erosion of International Society for Soil Mechanics and Geotechnical Engineering for the term 2018 to 2021. He is a member in H4 Committee on Embankment, Ground Improvement and Drainage Committee of Indian Road Congress. He is serving as geotechnical expert in Dams Safety Committee, Water Resource Development, Government of AP Science 2022. He served as a National Executive Committee member of Indian Geotechnical Society during the period 2013 to 2020. He is serving as chairman of IGS Vishakhapatnam chapter and ICI Vizag chapter. He served as Dean, College Development Council, Andhra University, and Director, AU Development Center. Sir, presently he is serving as Director, Center for Industrial and Scientific Consultancy. We are truly honored to have Professor CNV Satyanarayan Reddy Garu with us today to share his vast experience and valuable insights into geosynthetics in sustainable constructions. Sir, may I now hand it over the session to you, sir. Thank you, sir.
Thank you. Thank you, Sridevi, for your patient introduction, reading out many
Thank
of
you, sir.
my achievements. So,
Sir, good
thank you,
evening,
sir.
sir.
yeah, good evening, sir.
Sir, myself Giridhar, sir.
Yeah, Giridhar, yeah.
Sir, if you don't mind, పైన screen share ఉన్నది కదా, sir. Annotate, slide control, slide show meeting, and more.
Is not,
Sir,
Yes,
cursor
sir.
పైకి తీసుకువెళ్తే వస్తుంది, sir. Your screen is sharing అన్నది కదా, sir. ఆ పైకి కర్సర్ తీసుకువెళ్తే slide controls, show meeting, more అన్నది.
1 minute, just a minute.
మౌస్ కర్సర్ పైకి డ్రాగ్ చేసి పైకి తీసుకువెళ్తే సార్ పైనుంచి ఒక పాపప్ కిందకు వస్తుంది సార్.
So here view everything is there. Just now is it okay? Can you see the slides?
స్లైడ్ కనిపిస్తుంది సార్. అంటే
What is the issue?
ఎవరైనా స్క్రిబుల్ చేసే ఛాన్సెస్ ఉంటాయి సార్. మీరు డిజేబుల్ యానోటేషన్ ఫర్ అదర్స్ అని అంటే ఇంకా ఎవరు
disable annotations.
సార్ ఆ పైన జస్ట్ కర్సర్ పైకి తీసుకువెళ్తే సార్
ఇక్కడ nothing
పాజ్
is
లేఅవుట్ యానోటేట్
View. Let me see. More, under more
Yes,
it will
sir.
be there.
More.
Yeah, I'll see. Okay.
Disable
Disable
and
annotate. Okay. Good.
disable annotate for others.
Yeah, that is
Yes, sir.
done.
Over, sir. Oh,
Can I
thank you
proceed?
very much.
Yeah.
Okay, sir.
So,
Thank you,
okay.
sir.
Okay. So, good evening to all of you.
Good evening, sir.
Yeah, good evening. So, I'll be taking about 1 hour, right? About 20 minutes for giving my talk on geosynthetics for sustainable constructions. So, in first half of my lecture, I'll be exposing you to various geosynthetic materials. I'll explain, right, what are the different geosynthetic materials and what functions they can perform, and then I'll discuss about the application of geosynthetics in sustainable constructions. So most of you may be aware of the term geosynthetics. So geosynthetics are the materials manufactured from polymers such as the polypropylene, polyethylene, polyester, PVC, nylon, etc. And these materials are meant for use with geological material like soil and rock, with the purpose of enhancing, improving, or modifying the behavior of the geomaterials for various civil engineering works. So these geosynthetics are available in a wide range of forms and materials. Materials in the sense, right, of the polymer from which they are made, each suiting to a slightly different application. So these materials have wide range of applications. So some of the applications you might have come across, they are used in construction of pavements, embankments, construction of retaining walls, construction of bridge abutments, formation of reservoir bunds, lining of bed of reservoirs, providing lining for canals, construction of dams, earthen dams, providing engineered landfills, strengthening of soft clay, where you need deep foundations. By strengthening soft clay using geosynthetic solution, you can manage with shallow foundation itself. Right. So I would like to mention you that whatever runway you have at Visakhapatnam, it is built on soft clay that is strengthened by geocomposite drains. Anyway, that also will be covering during course of lecture. You can use them for erosion control, sediment control, etc. So in this slide, you can see different types of geosynthetics. To name them: geotextiles, geogrids, geocells, geomembranes, geonets, then geocomposites. In fact, geosynthetic clay liner will be also categorized, right, as one of the geocomposite material. Only difference is the other geocomposites will have combination of two different geosynthetic materials, whereas in case of geosynthetic clay liner, you will have a bentonite packed in between geotextiles. Okay, so geonets and geoforms. So first I'll start with geotextile. So these geotextiles are flexible, permeable fabrics made of polymers, which can perform the functions of separation, filtration, reinforcement, and drainage. So these geotextiles are porous and they allow for both in plane and cross plane permeability. Right? They allow seepage of water along its plane as well as across its plane. So it will be useful for serving as drain and filter based on this ability. So among the various geosynthetics, geotextile is the most widely used geosynthetic material. It is available in rolls of 5 to 6 meter width and lengths varying from 50 to 150 meter. So just like how you show, how you see our conventional, right, cloths, fabrics in cloth showrooms, right? So how they are available in the form of rolls, right? Geotextiles are supplied just like rolls of varying width and varying lengths. So coming to geotextiles, you can categorize them as woven geotextiles and non-woven geotextiles. So woven geotextile is manufactured by the conventional method of weaving. So microscopic view, if you see, you can see the right weaving pattern. So you will have uniform pores, and pores are direct. If you hold the fabric against light, you can directly see, right, the pores available in the fabric. These woven geotextiles have high tensile strength and stiffness compared to non-wovens. So non-woven, right, the name itself indicates non-woven geotextile is manufactured by methods other than weaving. They are manufactured by heat bonding, resin bonding, or needle punching of a bunch of synthetic filaments or yarns. You don't see any visible thread pattern. Microscopic view appears like this. These non-woven geotextiles are thicker and they have irregular pores, right? These non-woven geotextiles have low tensile strength and low stiffness, so they are not preferred as reinforcement. You can use them as separators, drain and filter. Okay. Whereas the woven geotextile, you can use as reinforcement beside having the functions of separation, filtration, and drainage. So next type of geosynthetic material is geogrid. So geogrid is synthetic material manufactured by using high density polyethylene. So HDPE sheet will be punched, right? Holes will be punched into the sheet, and then the sheet will be stretched in two directions so as to produce, right, a geogrid of aperture, right, of this pattern, square pattern. This type of geogrid will be called as biaxial geogrid. If stretching, if you see the apertures with more elongation in one direction and less in other direction, you will call it as uniaxial geogrid. So you will have high tensile strength in the direction of longer, right, dimension of the aperture. In the transverse direction, the strength will be minimum. Particularly when use geogrid to reinforce soil supporting a retaining wall, right, you will go for uniaxial geogrid. Below footings, you will go for usage of biaxial geogrid. So anyway, so available forms beside uniaxial and biaxial, you have also triaxial geogrids, right? I'll tell you what is triaxial. The characteristic feature of geogrid is they mobilize their tensile strengths at very low strains. So they are right much stiffer compared to even woven geotextiles. So main function of geogrids is reinforcement. It cannot serve as separator because you have, right, large apertures. It cannot serve as filter and drain, right? Only function for which we use is reinforcing function. Right, so this is the picture of, right, uniaxial geogrid. So you will see, right, whenever you see apertures with more elongation in one direction and lesser in other direction, it means it is designed to provide a high tensile strength in one direction. Other direction, it will have nominal tensile strength. That is uniaxial. Biaxial, in both the directions, it possesses, right, the design tensile strength. Coming to triaxial geogrid, right? So the apertures are triangular in pattern. So compared to biaxial geogrid, triaxial geogrid can mobilize tensile strength more effectively, right? So whenever you want to use geogrid for basal reinforcement for supporting embankments on soils of low shear strength, you can think of, right, using triaxial geogrid. Similarly, below footings supported on reinforced soil beds also, you can prefer using triaxial geogrid compared to biaxial geogrid for more effectiveness. So I can see from here, uniaxial geogrid is a unidirectional structure with one-way stretch that provides strength in one direction only. Coming to biaxial geogrid, you have ribs that provide tensile strength in two perpendicular orthogonal directions. One direction, right, is named as mission direction and transfer direction. MD and TD they will mention if you look at specification of geogrids. Coming to triaxial geogrids, you have ribs oriented in three equilateral directions, offering more uniform tensile strength distribution across the grid. So in this table, you can see the application. As I said, uniaxial geogrid is meant for use where you will get strains only in one direction. If you take the case of foundation soil of a strip footing or retaining wall foundation soil, there you will use uniaxial geogrid. So whatever reinforced retaining walls you are seeing at the approaches of bridges or flyovers, there also you see usage of uniaxial geogrid only, right? So coming to biaxial geogrid, they will be preferred in embankment and road constructions. Coming to triaxial, soil stabilization in construction of heavy duty pavements and for laying pavements on soft ground or filled up ground, you prefer triaxial geogrid. So here you can see a picture of geogrid, right, placed over the subgrade for construction of a pavement. So geogrid either you can use at subgrade level between subgrade and subbase, or within subbase at interface of subbase and base course also you can use. When you provide geogrid, it will restrain lateral movement of the aggregator, right? Your subbase material. So when it restrains the materials from preventing lateral strains, its ability to support load will increase, right? So geonets. So you can see how geonets appear like this. These geonets are also called as geospacers. These are planar products. These materials consist of ribs in two directions. If you look at aperture size is right diamond shaped. Thickness of geonet is much more than that of geogrids. These geonets are made of stacked crisscrossing polymer strands which provide in-plane drainage. The main feature of geonet is to provide in-plane drainage. They allow water to flow along their plane. So if a geonet is consisting of two layers of polymer strands, it is called biplanar geonet. If it is containing three layers, it is called triplanar geonet. So the pictures of biplanar and triplanar geonets are shown. Cross section you can see, right? So here you have three layers of strands. So if you want to handle large volume of discharge when it is placed on steep slope, right? Then you will go for usage of triplanar. Don't think geonets are only used to prevent erosion on steeper slopes of embankment. You can as well place them within backfills and embankment material to help dissipation of pore water pressure, that is to drain out water during monsoon period. Right, the main purpose of geonet is drainage function. Unlike geogrids, they cannot serve as a reinforcing material. They are meant for drainage application. So wherever you are thinking of providing a material around drain and drain pipes, you will use a graded sand. If graded sand is not available, you can conjure using this geo net wrapping around the drain pipe. So you can use it to replace the traditional drainage layers. So applications, as I mentioned, you can use it for erosion control. So the ribs will act as small check dams, and they slow down surface runoff, and thereby you can control erosion. The geonet can serve as drainage, so water can flow along the plane of geonet because of its larger thickness, right? If you want to handle moderate discharge, you will go for right biplanar geonet, otherwise triplanar. So coming to the other type of geodesic material, geomembrane, it is an impervious synthetic fabric made from high density polyethylene, right? We generally mention HDPE membrane, right? So these fabrics are used to control fluid or gas flow. Suppose you are going for construction of a new canal. So generally lining for canal will be provided in areas where there is presence of highly pervious soil. Even otherwise also these days we are preferring to go for lined canals to minimize the seepage and to allow flow of water at a relatively higher speed. Right? In such a case, instead of going for cement concrete lining, you can simply use these geomembranes. You can place membranes along the sides and right bed of the canal to prevent seepage of water into underground. So these geomembranes are available in varying thicknesses as low as 0.5 mm to 3 mm thickness. So as mentioned, you can use as liner in canals and also landfill systems. So wherever you dump waste material, whether it is hazardous or non-hazardous, you will provide a base lining system so as to prevent leachate to seep into underground and pollute underground soil and underground and water, right? So there also you can use geomembranes. I'll show in next slide how it will be used in landfill system. You can also use geomembranes as dam-proof courses in floors and roofs. So black colored, if at all you see membrane in black color, if you understand that it is coated with the black carbon. Such material, even if it is exposed to sunlight, it does not get decayed under ultraviolet rays. So as long as any synthetic material is provided below ground surface, not directly exposed to sunlight, no black carbon treatment is required. In any application, if your material is likely to be exposed to sunlight, you need to use black carbon coated ones, right? So if you see the engineered land fill containing municipal solid waste or any non-hazardous right waste material, it will consist of a single composite liner system. So before dumping waste, what you do is on the existing subgrade, you will place compacted clay, right, of 450 to 600 mm thickness, and above that you will keep HDPE geomembrane of minimum 2 mm thickness, and above that you will keep an non-woven geotextile as a cushion over membrane, and above that you will place drainage material, graded sand, and in that layer you will provide perforated pipes for collection of leachate, right? So above that you will have waste material dumped. That means when waste material gets decomposed and leachate is formed, so that will be collected into this drainage layer, graded sand, and it will be flowing into these perforated right drainage pipes, and it will be discharged into separately provided sums. So no leachate can seep into underground because you have a geomembrane here. Even if geomembrane has defect somewhere at any place, also underlying that you have again clay liner, right? So you are taking right too much care. You are providing membrane and underneath that clay liner, such that no leachate will reach to underground soil and pollute soil as well as groundwater, right? So in such lining systems of engineered landfills, you will use geomembranes, right? So always whenever geomembrane is used, don't put coarse grained material above it. It will damage, right, the geomembrane. So to protect it, you need to place a cushioning layer, nano geotextile above it, right? That is the function of nano geotextile here. So if it is a landfill meant for storing, right, hazardous waste, right, some industrial waste, if it is found hazardous, in such a case, you will provide a double composite liner. So whatever layers we have shown in single composite liner, so we repeat it, right? So we provide a double, right, composite liner system. Even if the layers in first layer fail, second layer will be there to prevent leachate entry into underground, right? So that is the only difference. So I don't want to discuss much about it. Keep in mind that the geosynthetics are used in base lining system of engineered landfills. Here, not only geomembrane you are using, along with it for cushioning you are using non-woven geotextile. So similarly, when waste is contained, so it will be contained by forming a bund, right? Bund all around the facility. So inside slope of bund, if you see, right, on inside slope of the bunds of landfill, can you place whatever a single composite liner or double composite liner system I have shown? Can you place clay on slope and compact it properly? Difficult. At the bottom, at the base, you can do it, right? On the inner slope of bund, you need to provide alternate material to this compacted clay liner, right? So as alternate to this, we will use GCL, right? Geosynthetic clay liner, wherein bentonite powder is packed in between two geotextiles. So that will be simply placed on the inner slope of the bund, and the rest of the layers will be as it is. The only thing is clay will be replaced with GCL. So GCL performs the same function as that of compacted clay. Okay, so I'll come to, right, geocentric clay liner. As said, it consists of bentonite clay packed between geotextiles to serve as impervious barrier. Its coefficient of permeability will be between 10 power minus 10 to 10 power minus 12, right, centimeter per second. Its main application is in landfill construction. Next geosynthetic material is geocell. So these geocells are three-dimensional honeycomb-like structures made of strips of polymer sheets, right? So polymer sheet strips will be used to form, right, cells, and these cells will be filled with some selected coarse grain material. It can be good quality morum soil, or it can be with a GSB material like this, right? So when you fill these cells with such free draining, right, coarse grain material, it can serve as a basal reinforcement, and it will help in load transfer, right, over a larger area. So you can see the characteristics. These geocells enable containment of depth of soil and helps in load transmission. You can use geocell with infill as basal reinforcement for construction of roads, construction of embankments over weak subgrades. So it will distribute the weight of embankment non-uniform, right, load coming from the base of embankment uniformly to weak subgrade by provision of geocell layers. You can also provide the geocells on steep slopes of embankments or existing steep slopes of hills comprising of right earth to check erosion. So you can see here geocell is placed on right existing slope with the objective of controlling soil erosion here. So here you can see here right a baby chip aggregate is put into the cells, and such layer when it is placed at the subgrade level, it will serve as a basal reinforcement for the pavement. Similarly, when you construct embankments also, you can provide geocells with infill, right? So the stiffness of geocell with infill can be used to reduce right stress on the underlying soil, and also it will be useful in uniform distribution of load onto subgrade. So the other geosynthetic material is geofoam. So most of you are exposed to foam concrete, right? So the advantage of your foam concrete is lightweight, right? So here also geofoam is manufactured into large lightweight blocks by polymeric expansion process. So geofoam blocks you can have. So the reason for lightweightedness of this geofoam material is right, you have voids the material which are filled with the gas. So if you look at density of geofoam, you'll be surprised. Its density is just 1 to 2% of density of soil with comparable strength. That means the load carrying ability of geofoam will be more or less equal to that of soil only, but coming to density, it is only 1 to 2% of it. Right? So that much lightweightedness we have for this geofoam. So this it is very easy to install in all weather conditions. Only drawback is these geofoam blocks, right? Whatever you use, they will be affected when they get contact with the petroleum solvents, right? As they react and get transformed into glue type substance, and thereafter they cannot support any load. Similarly, untreated geofoam is susceptible to fire hazard. So the blocks prepared from geofoam you can use for construction of lightweight embankments on weak soils. Similarly, in preparation of subgrade for preparing pavements where top layers of soil is comprised of soft clay. And also you can use geofoam material as backfill behind retaining walls to reduce lateral thrust on the retaining walls. So geocomposites, as I told, these are combinations of two different kinds of geosynthetics to get advantages of each of the materials, right? You can see usage of geotextile, geonet together, geotextile, geomembrane together, that you have seen in landfill, geotextile, geogrid together. If you want a reinforcing material of high strength to be used on clay subgrade for laying of railway track or highway, so geogrid cannot serve as separator. So it allows intermixing of subbase material and subgrade. Or in case of railway track, ballast gets mixed with subgrade, right? So to prevent that, if you place geogrid with geotextile, right, it will be preventing intermixing of overlying and underlying material, right? So like that. Similarly, geomembrane, geogrid together you can use where you want to prevent migration of capillary water into overlying layers. Then you can conjure using geomembrane with geogrid. So like that. One more geocomposite of importance is geotextile polymer core composite, right? That is called PVD, prefabricated vertical drain. So for drainage, for providing right effective drainage of soft clays, we provide vertical drains in the form of prefabricated vertical drains, right? So it is a geocomposite drain. I'll show the picture of it and show what is the benefit of using PVD. along with application of preload on surface of soft clay. The other geocomposite material is GCL, geosynthetic clay liner, that we have already discussed. So here I have tabulated to explain you and realize, right, what are the different functions each of the geosynthetic material can perform. So when you use any two materials together, you will get the combined right functions of those materials. So looking at the advantage of geosynthetics, they are cheaper, easy to transport, and installation is easy. You can design them for a given application. Installation can be done quickly without the necessity of skilled labor. So they are consistent over a wide range of soils. Space savings. If you go for conventional construction, it may be requiring right more space. With geosynthetics, you can construct the same facility with smaller space requirement. I'll show when we discuss about reinforced embankments. So material quality control. These materials are more homogeneous because they are machine made, factory made. So compared to natural materials, they are more homogeneous. So better quality control can be exercised at the site. So easy material deployment. They are less environmentally sensitive. They don't cause right any pollution to the subsoil when they are placed embedded in soil. They have improved performance. They are durable, and they can last long unless they are exposed to ultraviolet rays of sunlight. So they are compatible with field conditions. That means you can use geosynthetic materials in soils, alkaline soils, no issue. Only acidic environment, if pH is below 2, you should not use them. Otherwise, you can say it can be used right for pH values above 2, up to even 7, 8, nothing will happen to them. Okay. So since you are attending this FDP for the last, I think 4 days, right? You are exposed to sustainable constructions. So what do you aim in sustainable constructions, right? So whenever you think of sustainable construction, you should employ right eco-friendly practices. Mainly you should target at right this one, savings in carbon footprints. Your construction shall minimize negative environmental impacts. It shall minimize social impacts, and it should reduce demand on conventional construction materials. And you should think of efficient use of local available materials. And the construction should result in long-term cost savings through durability and performance. It should involve innovative technologies. Okay. Okay. So now I'll discuss about some of the sustainable constructions you can have with the geosynthetics. So first thing I have mentioned here is strengthening of soft clay. That is strengthening of soft clay. How can you achieve? Strengthening of loose sand, if I say. Strengthening of loose sand is possible only by densifying it. We should consider, right, subjecting it to heavy damping or by adopting vibroflotation, inducing vibrations, or transmitting impact energy will result in densification of sand grains. Can you think of such methods in soft clay? Inducing vibrations does not strengthen soft clay because softening of clay is due to presence of more water in its voids. So in order to strengthen, you need to consolidate it. That means you have to drive pore water from the clay deposit, right? So strengthening of soft clay will achieve through pre-consolidation by installing prefabricated vertical drains and then by applying preload. Unless you apply load, pore water pressure does not increase and water tries to go out of the voids. When you place preload, pore water pressure will increase and it will try to get discharged into these provided prefabricated vertical drains, and from there it will be getting discharged into surface sand blanket which will provide. Okay, so anyway, we'll see that. And the other sustainable constructions which you can think with geosynthetics are reinforced earth retaining walls, reinforced embankments, reinforced soil beds, reinforced foundation mattress, and reinforced pavements. I'll discuss one after the other. Suppose I have soft clay deposit and I want to construct a facility there, right? For example, Visakhapatnam airport you can take. So there you have presence of thick deposits of soft clay extending to 14 to 18 meter depth. So at present, right, expansion work for parallel taxiways is going on. So there you cannot directly go for laying of your taxiway pavement because the N values of existing clay are as low as 1, 2, 3, right? And hardly we'll see value of N equal to 6 or 8 at 10 to 12 meter depth. At some places, even up to 16, 18 meter also, N values are only 3 and 4. Right? So without strengthening such soft clay, you cannot lay your pavement there. Right? Earlier also, for runway also, strengthening of soft clay was done using PVDs and by application of preload. So without improving drainage conditions over the existing soft clay, if I place a preload simulating the loading from my proposed structure, will it be of any use? No doubt pore water pressure will be increased, but for dissipating excess pore water pressure, water has to travel either in upward direction or downward direction depending upon availability of drainage space. Right, so it is as good as constructing your structure only. And moreover, because of very soft to soft consistency, even you cannot place the entire preload also. First thing, it will take very long time for consolidation, several years. Second thing, you will not be able to place entire preload. It will result in shear failure of soil. So in such soil, if I provide vertical drains, earlier initial form of vertical drain is simply boreholes made into clay deposit filled with clean graded sand. They are called sand drains. Now those sand drains are replaced by geocomposite drains, which we call them as the PVDs, prefabricated vertical drains. So suppose if you install a vertical drain, either in the form of sand drain or our geocomposite drain, and then apply preload in stages. Stage by stage, we place load. What will happen under the placed preload? Pore water pressure will rise, and now pore water need not travel in vertical direction. Since vertical drains are provided at a closer spacing, water can easily get discharged into these drains. And at surface, connecting all these vertical drains will provide a sand blanket, and water collected from each of these drains will be discharged into that layer. And within that layer, we will provide perforated drainage pipes. They will collect water and discharge into nearby drain. Right? So here, the advantage is, what is the drainage path when water is flowing radially? Suppose if vertical drains are placed at 1 to 1.5 meter spacing. In radial flow, drainage path is only half of the spacing of the vertical drains. In the absence of vertical drains, the drainage path is, suppose clay is underlined by impervious layer, then drainage path is equal to thickness of the clay deposit. So you know that time taken for completion of given level of consolidation, right, depends on drainage path. Time required for consolidation is proportional to square of drainage path. You have the relation TV is equal to CVT by D square. Okay, for a given degree of consolidation, TV is constant. CV, coefficient of consolidation, if you take it as constant, you can say small t, time for right, achieving a given level of consolidation is proportional to square of drainage path. In the absence of vertical drains, so T is proportional to D square, which is 10 meter, 12 meter, or 18 meter. When you provide vertical drains in radial drainage, for radial flow, drainage path is only, if spacing is 1.5, drainage path is 0.75. So the time required for completion of consolidation decreases drastically, right? So that is the basic concept in providing these PVDs. So without drains, if you provide preload, it takes several years, right, for completion of consolidation. If you provide only drains, if you think that I provide drains, don't put any surcharge, water will flow into it. Only a little water which is in the immediate neighborhood may get drained out, right? So it also cannot achieve consolidation. If you provide drains and place preload in stages, you can complete consolidation in a period of 6 to 9 months. After 9 months, you can lay your right runway or taxiway, or you can construct light to moderate structures using shallow foundations. Right, where you cannot walk, soil in which you cannot walk, there it is possible to construct a structure of light to moderate load by strengthening using these PVDs by application of preload. So this is how a PVD looks. So this prefabricated vertical drain comprises an inner core made of high quality flexible polypropylene with water channels. These corrugations are channels. They will be helpful once water enters inside this drain. Water gets drained along these channels and get discharged into surface sand blanket which you provide, and before placing preload. So this inner core is wrapped in a non-woven geotextile. So here you have inner plastic core and outer you have non-woven geotextile. So it is a geocomposite. So you will be wondering how this geocomposite drain will be inserted or installed into the ground. It will be flexible because plastic sheet is flexible. Non-woven geotextile is flexible. Non-woven geotextile will appear like your winter cloth, whatever rug you will use to protect from cold temperatures, it will appear like that, right? If you hold against light, you will not see any direct pores. But if you pour water on one side, it will come through other side. That means it is porous, right? So the purpose of this wrapping non-woven geotextile around core is to serve as filter. When water from neighboring soil enters, all fines will be blocked and only water will be allowed to enter inside, and that water flows along these channels. So for installation of these strip drains, you will use a lighter rig called stitcher. So for installation of strip drain, you will make use of steel lance and base plate. I'll show. So steel lance is a hollow steel right, section having cross section slightly bigger than cross section of your PVD. Length of steel lance shall be equal to depth up to which you want to install PVD. Right, so these PVDs are available in the form of rolls, just like you see ribbon rolls in Kangan halls. These right strip drains will be available in the form of rolls. So one end of the strip drain you insert from top cross section of steel lance and push it till it comes from the bottom. When it comes from bottom cross section of steel lance, there you place this base plate with a central hook. So insert the strip drain through this right hook and fold it back and staple. And when you hold strip drain at top, this base plate will close the bottom, right, the bottom of the steel lance. So place base plate steel lands with strip drain inside on surface of soft clay and push it into ground by applying static pressure. So your strip drain will get unrolled from the roll, and steel lands along with base plate with strip drain inside penetrates into ground. After having pushed steel lands up to the required depth, what you will do? Leaving a little portion of strip drain above, because you need to embed that into sand blanket. You cut it. After cutting, you take out this steel lands. This base plate will be remaining inside the ground, right? You cannot retrieve your base plate. That is how these strip drains, PVDs, are installed. You can see here, right? So this is base plate with central right hook. So this is the strip your PVD, right? It is taken through the central hook, folded back and stapled. This is steel lands which you are seeing. So here you can see, right? These are the cut PVDs after installation into ground. So here you can see, right, a roll from which, right, PVD is being installed at another location. So all those heads of PVDs will be embedded in the clay, and you will place preload. Preload is, you can simply dump some gravelly soil in the form of an embankment in stages. Suppose I want to bring safe bearing capacity of my ground to 10 ton per meter square. You need to stack a material, gravelly soil, to a height of 5 meter, because the density of gravel or moram soil is 2 ton per meter cube. So don't put 5 tons at once. You estimate what is the ultimate bearing capacity of soft clay. If it is say 4 ton per meter square. So first stage you place moram to a height of about 1.5, so that induced stress is 3 ton per meter square, does not cause any shear failure. Once it gets consolidated, when no further settlement of preload you see, or else you can insert piezometers and see pore water pressure. If excess pore water pressure is completely dissipated, then you place another 1.5 meter of soil. Like that, in stages, you will apply preload and achieve consolidation of clay under applied preload intensity. For construction of your actual structure, what you will do? You will remove the placed preload and immediately take up your construction, right? So without going for this method, if at all I want to lay a runway here, soft clay is present to deeper depth. So I should construct a bridge there, right, to support a runway by adopting piles and terminating them in rock strata. Whereas I am able to consolidate existing right soft clay layer and able to go for conventional right flexible runway, right, by conventional sub-base, base layers and bituminous surfacing. I am able to construct, right? So if I am going for a cement concrete runway supported on pile foundation, so how much volume of concrete will be required, how much amount of steel will be required, right? So I am avoiding that, right? So I am having tremendous, right, significant savings in carbon footprint, because I am avoiding usage of concrete and steel here. So this is one sustainable practice. So the other application, which majority of you might have seen, is reinforced retaining walls. Now, wherever you see construction of a flyover, in the approach of flyover, you see construction of this reinforced retaining wall. When you walk by the side of a flyover, constructed flyover, you will see beautiful, beautifully assembled precast concrete members. They are called fascia panels, right? So fascia wall is constructed using precast concrete panels. They are placed one by the side of the other, one above the other. By interlocking, the wall is formed. And before constructing that fascia wall, you will simply put a bed concrete, right? And that we call as leveling pad. No special foundation is required. Simply place leveling pad, bed concrete, and above that you start placing your fascia panel members, right? On the back of fascia panel members, there will be arrangement for attaching the reinforcing material. It can be high stiffness geotextile, or in majority of cases you will see uniaxial geogrids. And what is the construction material that is used here? You will use selected granular material. It can be crusher dust. Initially, they used to use river sand and good quality morum soils. Now, due to increased demand and scarcity of those materials, we are going for usage of crusher dust. Even fly ash is also being used, right? So whatever select material you use to construct retaining wall in combination with the reinforcing material, right? That material is called fill. The soil which you are retaining with your reinforced retaining wall is called backfill. Existing soil which you are retaining is backfill, right? The material used to construct the retaining wall is called fill. So don't get confused between the terms fill and backfill. Okay. So in the absence of these reinforced retaining walls earlier, in the bridge approaches, they used to construct conventional retaining walls, either gravity retaining walls or cantilever retaining wall or counterfort retaining walls, right? To contain soil of varying height from starting point of the bridge up to central portion. So in bridge approach, they used to have usage of large volumes of concrete and steel in construction of conventional retaining walls. Now, everywhere we are going for construction of these reinforced retaining walls. So no concrete except for fascia panels, right? No steel. Most of the construction material is fill, right? It can be morum soil if it is local available, or it can be a byproduct generated at rock crushing plants like crusher dust, even pond ash, bottom ash, fly ash, they can be used, right? Any granular material which is non-hazardous can be used. So coming to cost of reinforced retaining wall, it is economical by about 30 to 40% compared to conventional retaining wall, right? So when you are using some industrial byproduct as fill materials, some more additional saving you are getting, right? So in doing so, you are avoiding usage of concrete and steel, right? Reducing usage of them, right? So carbon emissions will be increased. Okay. Not only that, this reinforced retaining wall is a flexible construction, right? Involving fill and synthetic reinforcement. So if any structure is flexible, its ability to resist earthquakes, right? Ground shaking, whatever unbalanced forces that will arise due to ground shaking, right? These flexible structures can sustain, right, such forces well compared to rigid structures. That's why reinforced retaining walls have better seismic resistance compared to conventional retaining walls. So you can see some pictures of retaining walls. Even geocells with infill can be placed one above the other to construct a retaining wall. Right. So this type of retaining wall you are seeing opposite Sivarama Sweets in Visakhapatnam. Almost in every town and city, present day, wherever flyover construction is going on, they are going for construction of retaining walls in approaches using reinforced technology. So different types of fascia panels, right, to improve aesthetic appearance, right, have come into use. Even single panel fascia is also available. So most of you might have gone to Vijayawada Kanakadurga temple. So there, for widening the existing Ghat road, they have constructed a two-tier reinforced retaining wall in 2008. The maximum height of constructed wall was 22.5 meters. Even now, if you have not paid attention, if you go, just have a watch, right, on this constructed reinforced retaining wall. So whatever advantages I have mentioned, They are here. They take less time for construction, simple to construct, cost effective. So you can use industrial byproducts as fill material. Being flexible, sustain seismic loading. One more advantage is, if I want to construct conventional retaining wall of say 6 or 8 meter high, the required bearing capacity of soil will be more than 30 ton per meter square. Whereas for this reinforced earth retaining wall, the required safe bearing capacity of soil will be around 20 to 22 ton per meter square. That means relatively soils with relatively lower bearing capacity will be sufficient for constructing a retaining wall of given height, right? Compared to conventional walls, the requirement of bearing capacity of soil for RE wall is less. Okay. And one more thing is, suppose without retaining wall, you want to construct, you propose to construct a natural embankment using soil only. Then what you have to do? You have to construct embankment with safe side slopes. So that requires additional space, right? In urban areas, you will not get that much space to adopt a safe slope for your earthen embankment band, right? So in such a case also, using reinforced earth retaining wall, you can construct wall with vertical face, right? So the required width for supporting roadway of a given width, right, is drastically reduced. So how much pavement width is there and how much shoulder width is there? Only that much base width is there. You are not going beyond that, right? So enable providing bridge approaches with lesser base width compared to conventional types or compared to earthen embankments. Next, coming to embankment, right? Embankments are used to support right highways and railway tracks, particularly in low-lying right areas. So whenever you construct embankment, earlier days we used to construct only embankments using suitable soils by providing a relatively flatter slope, so that no failure of no sliding of soil occurs in the vicinity of slope, right? Now, with the present day developments in reinforced earth area, we are going for construction of reinforced embankments, right? You can provide reinforcement in layers in the vicinity of slope region, and thereby not only you can steepen the slope, but also you can have increased load carrying capacity, because the reinforcing layers will prevent movement of soil, right, in outward direction under the placed load. When loads are applied by the moving vehicles, tensile strains will be developed in outward direction. So the outward movement tendency is prevented by the placed reinforcement layers by the way of its interaction with soil through friction and adhesion. So you can see here, these two figures I have shown here to explain the benefit of placing reinforcement. So in both the cases, top width of embankment is same, height of embankment is same. In unreinforced case, you see the required base width is very large. By provision of reinforcement, the required base width can be reduced drastically, right? Particularly in urban areas where there is right restriction on space, you cannot go for unreinforced embankments, you have to go for it. Similarly, when you expand your highways or railways, also already some area with construction may be there. There also you may not go beyond a certain line, right? So in such a case also you can think of this. Even if adopting this much steeper slope is not possible, then the option is to go for construction of a RE wall. So when top width of embankment is small, whatever reinforcement you design for stability they will either overlap or approach each other. In such a case, you provide reinforcement extending from one slope to other slope like this. If width is more, then you can provide reinforcement only in the slope regions. Need not provide continuous reinforcement. These are different patterns of placing reinforcement in embankments. Okay, so whatever I have explained, I have put here. Okay, so they require less base width for given height of embankment. Okay, next one. Enable usage of marginal materials in highway embankment construction. Let me say, I have some materials with poor drainage conditions which do not meet the specification for building an embankment. In such a case, by placing geocomposites within such marginal materials, I can improve drainage conditions in the soil and I can make them suitable for use in embankment construction. For example, any granular material, can I use it in embankment construction? No. You need to have some bonding between the particles, otherwise it will not be stable. Right? By using geocentric sheets, even I can use a corrosionless material like sand, even fine sand. Right? I can place a geotextile, place certain thickness of sand, fold geotextile back, place another geotextile, put some more layer of sand, wrap geotextile back into the material like that, right? So by doing this wrapping technique, I am able to use even corrosionless material in embankment construction. Okay, so you need to properly design the wrap back, right, length of geotextile. Under load, it should not get pulled out, right? So keep in mind that the soil on which you cannot walk, there you can take your earth moving equipment, any crane, any truck, by simply spreading a layer of some granular material and placing geotextile over a larger area. What happens is when a truck moves on it, unless geotextile gets pulled in from the area, localized punching under the load cannot happen. Right? So in majority of construction sites where the top soil is slushy, they generally put some 2 to 3 inch thick crushed dust or sand, and above that they will place a sheet of geotextile, and then they allow the construction equipment to move on. Okay. Okay. So not only you can think of geosynthetic material in the form of geogrid or geocomposite, combination of textile and geogrid as reinforcement, but also on the side steeper slopes, if you place geonets, they will protect it from erosion of soil from steep slope, right? So that also you can think. Next one is reinforced foundation mattress. Sir, how much time I have? Oh, I think I have 10 more minutes.
Sir, 20 minutes.
20 minutes, okay, fine. So
Last
I think
5 minutes will be interactive
question answer. Okay,
question
okay.
answers.
So I'll try to finish in about 10 minutes or so, 10, 15 minutes.
15 minutes you are having time, sir. Last 5 minutes we are having that
Yeah,
session.
yeah. Okay, okay. So coming to reinforced foundation mattress, suppose you have a soft clay at a place, right? Based on its low shear strength or low undrained cohesion, it cannot support an embankment of height more than 2 meters. I want to construct an embankment of 3 to 4 meter height. In such a case, what I will do is, I will provide what is known as reinforced foundation mattress, right? The purpose of this reinforced foundation mattress is to spread the weight of my proposed embankment over a larger area. I'll show in figure. Okay. So for constructing embankment of larger height in soft clay, what we do is we prepare what is known as reinforced foundation mattress. This reinforced foundation mattress comprises of generally frictional fill, good quality gravel, or coso frictional fill, clay sand or clay gravel, provided with layers of high stiffness, high tensile strength geogrids. So keep in mind that in old literature they will say high stiffness, high strength geotext, high stiffness, high tensile strength reinforcing material is only geogrid. Now matching stiffness and matching high strength of geogrid, even geotextiles are being manufactured. Such high stiffness, high strength geotextiles were recently used in our Visakhapatnam airport, right? Runway expansion work, right? So present day, high stiffness, high tensile strength reinforcement means need not specifically mention geogrid. You can as well use geotextile also. But their production is right not as much as you have in case of geogrid, right? So maybe after 5-10 years, you will see geotextile, high stiffness, high tensile strength geotextiles dominating over geogrids. Time being, geogrids are being widely used, right? Due to their popularity in terms of their high stiffness and high tensile strength. So anyway, this reinforced foundation mattress will serve as a stiffening layer. Think that it is like a slab, RCC slab like thing, right? Frictional fill reinforced with the 2 layers of high stiffness, high tensile strength geogrids. Over this, if I place embankment, so embankment in central portion, the intensity of load transfer will be more, and as you move towards its toes, pressure will go on decreasing. Non-uniform pressure distribution will be there. Because of this provision of reinforced soil mattress, this non-uniform load distribution, by the time it gets transferred from the bottom of reinforced bed, it becomes uniform. And that too, the pressure will be transmitted over a larger width. Thereby, the intensity of pressure transferred to soft clay decreases. So the objective of foundation mattress is to distribute load uniformly over a larger area so as to avoid bearing capacity or shear failure and avoid defense settlements. So these reinforced foundation mattress consists of frictional or coso-frictional fill reinforced by high stiffness, high strength geotextiles or geotextiles placed on subgrade to support embankment, right? So they enable construction of embankments over weak subgrades, particularly on soft clays. What do you see in this slide? On soft clay, I am providing a reinforced foundation mattress, and above that I am constructing reinforced embankment, right? So instead of constructing unreinforced embankment, if I provide reinforced embankment, the load that will come onto reinforced foundation mattress can be reduced because you can steepen the slopes for a given height. The volume of the material of embankment will be less, right? So it is a most effective way of reducing load on soft clay. Adopting reinforced foundation mattress and then constructing reinforced embankment over it. Next, reinforced soil beds. Reinforced soil beds. Suppose at a place I have presence of soft clay with undrained corrosion of say 25 to 40 kN per meter square. If you calculate safe bearing capacity using your basic theory, our Indian Standard Code 1904, sorry, IS 6404, 6403, right, recommends usage of basics bearing capacity theory. If you calculate bearing capacity, it will be very low, between 3 to 5 ton per meter square. If you want to construct some G+3 or G+4 building, that bearing capacity will not be sufficient, right? In such a case, you should think of using deep foundation to support your columns. Suppose at a place hard strata is not present, even 20 meter, 30 meter also, you are getting clay of low shear strength only, N values of 3, 4, 5 only. In such a case, going for long piles, long frictional piles will be expensive. right? Your client, whoever comes to you for building G+2 or G+3 structure, if you recommend piles of length 20 to 25 meter, right, he cannot bear that. So in such a case, what you can do is, you replace the existing soft clay below the proposed foundation level up to a depth of at least equal to proposed size of footing. Suppose I am planning to use a foundation of size 1 or 1.2 meter to have a bearing capacity of 10 ton per meter square. Original soil bearing capacity is 3 to 5. It is not 10. But I would like to construct my structure by laying a foundation of size 1.2 meter with safe bearing capacity of 10 ton per meter square. To do that, what I will do is, below the proposed foundation level, generally foundation depth will be 1.5 to 2 meter below the ground surface, right? So below the foundation depth, proposed foundation depth, you excavate up to a depth of B. B means 1.2 meter. Remove soft clay and then prepare a foundation bed by placing frictional, that is granular, or coso-frictional. Coso-frictional means clay gravel, or clay sand. Clay sand means more of sand and with little clay binding, right? So such fill material you place. Best choice is go for poisonless or frictional fill, like crusher dust, river sand, good quality moram you take. You place a layer of say 30 to 45 centimeter, compact it. Then place a geogrid layer. Then again place frictional fill, compact it. Place another layer. Place frictional fill. Place another layer. Like 3 to 5 layers you can accommodate depending upon your proposed size and depth. Right? You will be preparing a foundation bed using frictional fill and by placing high stiffness, high tensile strength geogrid. So there is design for required bearing capacity, how much tensile strength reinforcement, depending upon number of layers you provide and spacing, it varies. Right? There is a methodology for it. So keep in mind that reinforced soil bed comprises of mostly frictional fill that is reinforced with 3 to 5 layers. So using such prepared reinforced soil bed, you can design your footing to a safe bearing capacity of 3 to 5 times the safe bearing capacity of native ground. Suppose my safe bearing capacity is 3 ton per meter square. So I can design the reinforced soil bed to support footings with the safe bearing capacity of 15 ton per meter square. Up to 5 times I can design. Okay. So I can avoid the necessity, right? I can avoid going for deep foundations. Okay. If you have to adopt pile foundations, long piles, so imagine how much volume of concrete and steel you have to provide, right? So simply by using synthetic reinforcement and frictional soil, you are able to resort to shallow foundation. So if anyone belongs to Machilipatnam, there Krishna University is there, right? So buildings in Krishna University, G+3, G+4, they have been constructed in soft clay using reinforced soil bed, right? So you can adopt these technologies, right, for supporting structures in soils of low bearing capacity. So section appears like this. So up to 1 to 1.2 times proposed size, you will replace existing soil with the frictional fill reinforced with 3 to 5 layers of reinforcement. The lateral extent to which replacement should be done shall extend generally 1.5 to 2.5 B from those of the footings. If you simply center and only in central portion, if you prepare bed, it is not sufficient. You have to extend it beyond it, right? So in design, all these parameters will come. So in design of reinforced soil structure, we teach to our students, right, in MTech program, there are designs for it. But keep in mind that it is possible to support even G+3 or G+4 structure in soft clay, which originally has bearing capacity of 3 to 5 ton per meter square, by adopting this reinforced soil bed technology. Next one is reinforced flexible payments. So whenever you design flexible payments, the soil parameter you look at it is CBR, right? So for expansive clays in saturated condition, if you determine soaked CBR, the value will be below 1 also. Even you will see values of 0.4, 0.6. In such a case, code says replace top, right, 1 meter depth in case of expansive soil with good depth, having CBR of 10. You will find what is the effective CBR and lay the payment. Right? Not only that, if you have any clays upgrade, not necessarily expansive clay, red clay or brown clay, if soaked CBR value is less, what is relation between design payment thickness and CBR value? Lower the CBR value, higher will be the required payment thickness. So if required design payment thickness is more, the cost of construction will be more, right? So in order to reduce the payment thickness, you can provide reinforcement at the level of subgrade, that is between subbase layer and subgrade, for reducing the design payment thickness. Not only that, if you don't provide any reinforcement which can function as separator, filter or drain, what will happen is in course of a service of the payment, the subbase layer and subgrade will get mixed up. Effective payment layer will decrease. Though you have designed based on soaked CBR value, intermixing will cause reduction effective payment thickness. And once it goes on decreasing, the deterioration of payment happens at a faster rate. Not only that, if water table rises to shallow depth during rainy season, capillary water will try to migrate from subgrade to overlying layers. If you place a geotextile reinforcement at subgrade or the clay, what does it do? It will drain capillary water and prevent it from moving into overlying layers and prevent it from reaching to surface course and avoids stripping of bitumen. Right? So all such advantages will be there, apart from reducing design payment thickness. So if I place geotextile simply at subgrade, do you think it will serve as reinforcement? Simple placement does not derive its reinforcing ability. If you place geotextile, you should hold geotextile fabric in position. Then only under the load, as it gets stretched, right, it will derive its tensile strength. If you don't hold it by anchorage into trenches, longitudinal trenches made, what will happen? Under the applied wheel loads, geotextile simply gets pulled in and it deforms according to the subgrade strength. If you are holding it by anchorage, it will derive its reinforcing ability. If you simply place, it will perform like separator, filter and as a drain only. For deriving reinforcement action, you need to hold in position by anchoring into longitudinal trenches. Okay. So having exposed to the potential of geosynthetic materials in sustainable constructions, you may have some doubt, right? What will be the lifespan of these geosynthetic materials, or which type of geosynthetic, right? As I mentioned, geosynthetics are available in market made from different polymers. So which polymer based geosynthetic material is durable? That you should know. So durability of geosynthetics mainly depend on the parent material from which they are made. So if you have geosynthetics made from nylon, such such fabrics will absorb water and result in reduced strength due to swelling. Similarly, polyester and polyaramide, they have good resistance to abrasion mechanical property is good. They are capable of resisting high temperatures, but they react with water and degrade in long run. Right. So in soil, alternate drying and wetting, right, occurs. There will be variation in moisture levels. Soil will be in saturated condition during rainy season. Winter partially saturated, summer dry, like that, right? So if it gets exposed to water, it will decay. Coming to polyamides, they have good mechanical characteristics, including resistance to abrasion, absolute imperviousness to rotting. They withstand high temperature. Even they also get deteriorated upon wetting. So all these polymers listed in the slide, namely nylon, polyester, polyamides, right, all deteriorate upon wetting. So if you have geosynthetics made from polypropylene or polyethylene, you see they are rot-proof, they exhibit less creep, they are not affected by water. This is main important aspect when you use geosynthetic in soils, and they are unaffected in presence of chemical reagents also. They have fair resistance to abrasion, but affected by high temperature. As long as I am burying geosynthetic within soil layer, they will not be subjected to very high temperature. So it is not a serious drawback. That is the reason why whatever geosynthetic material, geotextile or geogrid you find in the field, they are either made from polypropylene or polyethylene. Okay. So any synthetic material, irrespective of right, whether it is polypropylene, nylon, polyester, whatever it is, they completely deteriorate within weeks or months when exposed to ultraviolet rays. So if at all, suppose in construction of reinforced retaining wall, you are using geotextile sheet as reinforcement, the geotextile sheet will be wrapped back into fill to serve as facing. No separate fascia wall will be constructed. In such a case, the wrapped portion of geotextile is exposed to sunlight. Then you have to use black carbon coated geotextiles, right? So only that you should keep in mind. Right. So that's it I have. I don't want to conclude because I have discussed on many aspects. So I hope, right, I have brought out the things in a clear manner. Still, if you have any doubts, you are free to ask.
Thank you, sir. Thank you, Professor CNV Satyanarayan Reddy, sir, for your insightful and thought-provoking session on geosynthetics in sustainable construction. Your valuable inputs have greatly enriched our understanding of the subject, sir. Now we'll proceed to the interactive question and answer session. Participants who wish to ask questions may kindly ask questions, or they can post also in chat box. Hello, sir.
Yeah.
So one question is there, shall I ask, sir?
Yeah.
How can geosynthetics be used to improve the load capacity of foundation?
For that, I have to explain the concept of reinforced depth, right? So when you place reinforcement into soil, so when you apply load in vertical direction, right? So the soil particles or soil grains tend to move in outward direction, whereas the reinforcement layers prevent outward moving tendency of particles by restraining them, right? Through friction or adhesion mobilized at the interface. So when you restrict the movement of soil grains, right? When you prevent them from getting displaced under load, it is like additional confinement. In triaxial test, as sigma 3 increases, the capacity of soil to withstand stress in vertical direction, sigma 1 increases. Same is the case. Reinforcement provision in soils provides additional restraint onto overlying and underlying soil, thereby its load carrying capacity increases. Okay.
Thank you, sir. Participants can post their questions in the chat box. Thank you, sir. On behalf of the organizing committee and all participants, I sincerely express our gratitude to Professor CNV Satyanarayan Reddy, sir, for sparing his valuable time and sharing his rich expertise with us today. We also thank all participants for their active engagement throughout the session.
Okay, before leaving the session, I thank all the participants for their interest and for their patient listening. I know throughout the day they are busy and still they are logging in time to update their knowledge, right? So I congratulate all the participants for attending this important FDP, right? ATAL FDP. So thank you all. Madam,
Thank you,
can
sir.
I sign out?
Yes, sir. Sure, sir. Thank you, sir.
Okay. Bye to all of you.
With this, we conclude the first session of our ACT ATAL Faculty Development Program on Geosynthetics in Sustainable Constructions. We'll rejoin the next session shortly. Welcome to the session 2 of the day 5 of ACT ATAL Faculty Development Program on Sustainable Practices and Innovative Trends in Civil Engineering. Our next expert session is by Dr. M. Srinivasula Reddy, sir, Principal Structure Engineer, WSP Consultants Indian Private Limited, on development of structural geopolymer concrete using various industrial waste. Before we begin, I now invite our faculty colleague, Mr. DVV Satyanarayana, Assistant Professor, to formally introduce our eminent speaker to the audience. Over to you, sir.
Thank you, ma'am. Can you hear me?
Yes, sir.
Good evening, dignitaries, participants, and my dear colleagues. I feel privileged to introduce you all Dr. M. Srinivasula Reddy. He holds bachelor's degree in civil engineering from Sri Venkateswara University Affiliated College, Andhra Pradesh, in the year 2001-2005. He has done his master's in structural engineering from IIT Roorkee in the year 2005-2007 and doctoral degree from IIT Bhubaneswar in the year 2015-2018. Dr. Reddy is currently working as Senior Principal Structural Engineer in an MNC Bangalore. He has experience in both academics and industry. He worked as an Associate Professor and R&D in charge at GPRSC Autonomous, Kurnool, Andhra Pradesh. Prior to this, he worked as a technical specialist in civil structural works at Wipro Limited, Bangalore. Senior Structural Engineer at Daral Hansa, Pune, and Assistant Manager in the Design Division at Reliance Navi Mumbai, SES Private Limited, Navi Mumbai. He has been active in structural design of multi-storied buildings, largely of concrete structures, structural design, and wetting of various structures as a consultant. In addition, he largely does research on green concrete, geopolymer concrete, concrete development using industrial waste, and mixed design development in the area of advanced concrete technology. He has 35 international journals and 12 conference papers to his credit. He also guided 18 students in their master's research. He is very active consultant for the structural project works in the fields of analysis, design, and vetting. His research interests include concrete technology, characterization of cementitious materials, geopolymer concrete, structural health monitoring, and NDT of existing construction materials. Now we warmly welcome you, sir, for your presentation. Thank you, ma'am. Over to you, ma'am.
Thank you, Satyanarayana.
Sir, we are delighted to have you here, sir, and we look forward to your talk, sir. Over to you, sir.
Thank you, madam. And shall I share my screen, madam?
Yes, sir.
Okay.
Good evening, sir.
Hello.
Good evening, sir.
Hello, sir.
Good day.
Sir, myself Giridhar.
Hello, Giridhar.
Yeah,
Oh,
myself Giridhar from Bulaya College. Sir, a small thing. There is a option called more there. Like if you take your cursor to top,
mm,
I'm not there. To the top,
oh,
extreme top.
okay. Yeah,
I mean,
view is there.
your screen share is there, right?
I already
It's a
sharing my
green one,
screen.
green one.
No, no, I am already sharing. Wait,
Yeah,
let me.
right, sir. We have to, I mean, disable the annotates to others.
Okay, okay. Yeah.
So if you take your cursor to top, then there will be some options like at the
YouTube is there, view
not there.
is there.
You have to take your cursor to your screen is sharing.
Bottom right, bottom right. More is there at the
No,
bottom
sir,
right
no,
for
sir.
me.
At top, if you go there, your screen is sharing, right?
Yeah,
Yeah, if you take your cursor to that green tab,
yeah.
yeah, then there will be some pop-up comes. Yeah, there, disabled for others. Yeah. Thank you very much,
Yeah.
sir. Thank you,
Okay.
sir.
Yeah. Thank you. Shall I start then? Shall I
Yes, sir.
continue?
You can start, sir.
Okay. Thank you, madam, and thank you, Satyanarayana sir, for your nice introduction. And I think I can straight on go to my session. So, yeah, today I'm going to discuss about the development, like on the performance evaluation of structural geopower concrete made using various industrial waste. Let me see full screen. Yeah. So myself, Dr. M. Srinivas Reddy, and I'm currently working as a senior principal structural engineer in an MNC in Bangalore. Prior to this, I was working with Florida Engineering College, and before that, I was working in industry. Okay, this is a short introduction about me. Yeah, so today we'll discuss about first development part, and after that, the performance evaluation of the developed geopower concrete using the mixed design that we developed in our laboratory. So this how my presentation goes. So introduction about the present topic, scope, the B program, the material characterization, the various materials are used in this study, the mixed design development, which is the main core of this research, and the study of various properties like mechanical, durability, and microstructure, and finally my conclusions on my the research. Okay, so yeah, this is not a new topic. It's like so many years people are working on geopolymer concrete. So many people are using many different of waste materials, uh, and so like that, I also started my research trying with different waste materials. So in my research, I mostly concentrated on using these three uh, waste materials, that is fly ash, blast furnace iron slag, and red mud. So I don't need to explain much about fly ash and slag. So this fly ash is generally we get from thermal power stations where coal is used as a fuel for burning, and the iron slag. So you get from the iron industries. Then red mud. This red mud is generally we get from like aluminum industry. It is a byproduct of bauxite ore. So you can see here the picture says why they named it as a red mud. It looks like mud which is red in color, and because mainly this red color is due to the presence of a large amount of iron oxide in the material as a composition. So this using these three materials, actually I try to develop a mixed design, and I think most of you people know the mixed design. Many have like different researchers propose different mixed designs, and prior I start my research on this, I found many are using only trial and error method, like by considering 70% aggregate and 30% as a binder material. So likewise in this percentage wise, so it's like trial and error. It's not like so they are not considering any like properties of the material used or the specific gravity or physical properties or chemical properties. We can say the oxide composition. So most of those mixed agents, they are not used the composition and as well as the specific gravity details into account while developing their mixed design. So in this research, what I considered is I considered the composition uh, of the binder material use. It's not directly, indirectly. And the other thing is the specific gravity, which we generally use for the absolute volume method. Whenever we do some mixed design for M30 or M35, in general, what we use, we generally take the specific gravity of the what are all the materials we are using. Then we'll decide the water to cement ratio there. So in the similar way, I also developed the mixed design, which follows the ACI strength versus water to cement ratio curve, where if you want to target some strength, there will be corresponding water to cement ratio. So if suppose you are having fixed water to cement ratio, what will be your targeted strength? So in that way, in the same vein, I have considered the same concept to develop for geopolymer concrete also. So it will be easy to for everyone to follow instead of going for the trial and error approach. This gives like more methodological type of mixed design. Yeah. So you know that fly ash, this is utilization ratios. Maybe it might have increased little bit. So it was like maybe you can say some 4 5 years back. This is the data. So this data, like as per this data, fly ash percentage utilization is around 63 to 64%, and remaining 37% is left unutilized. And if we come to slag, 80% is utilized, because of this uh, Portland slag cement. So most of that waste material goes into that cement industry, and they use that as a slag for manufacturing PSC concrete cements. So that's why utilization of this slag is more, 80%. Then if you see the red mud, utilization is very, very, very less. So we can say only 3% worldwide. So yeah, so these three contributes to the mixed design of my research. Okay. So why we need this study is, yeah, to dump all this waste we need like huge storage area, and maintaining that storage area also is like cost intensive. And moreover, the other than this like maintenance and land utilization purpose, if you uh, leave that aside because of plenty of land. But the major problem with this fly ash and red mud is that it contaminates the groundwater, soil, and air in the nearby premises. So because of the leachate generation from these two materials. And so this is the main reason for the for like people going for the geopolymer concrete to reduce the like contamination or to reduce the environmental pollution. And that is one part why we need to use these waste materials only. But on the other hand, if you see, everyone knows this, that for every 1 ton of cement production, an equal amount, almost equal amount of carbon dioxide will be emitted. So so uh, at one stage we can do both. You can reduce the carbon emissions from the cement industry and or from the construction industry, and you can utilize the unutilized like industrial waste, which otherwise will contaminate the environment. So with this geopolymer concrete, we can both serve the serve the people by reducing the carbon dioxide, and as well as them reducing utilizing the like most of the unutilized industrial waste. So because of the reason, this geopower technology is like nowadays. So I think so many even other metals also uh, used people to develop the geopolymer concrete. So I will discuss about that also. Generally, what type of industrial waste is suitable for geopolymer? So that is also very important, because we cannot use all the whatever the waste material we are having. There will be some logic behind that. So that also we'll discuss. Yeah, so it's a general definition. It's a green concrete does not depend on the presence of Portland cement as a binder. Instead, it requires activation of source materials rich in silicates and aluminates using alkali activator solution. So we generally, alkali activator solution, we generally use sodium or potassium hydroxide or sodium or potassium silicate. So these are like the cubes which I developed using the various like industrial waste. So first one, if you see, this is purely using fly ash, and this one is the combination of fly ash, red mud, and GGBS. And third one is like fly ash and GGBS. So these three are like three different type of composition. One with fly ash alone, one with fly ash and slag like the GGBS, and the other is fly ash, GGBS, and red mud. You can see here red mud. Red mud I used only 20%, but you see the color even with for 20%. In this means the binder itself will be roughly it will, we can say 35% will be the binder. If out of the 35%, 20% means only 7%, but it gives a beautiful color because of the most large amount of iron oxides present in that red mud used. Okay, so I'm going fast, or the pace is okay.
Okay, sir.
Okay. So this geopolymerization mechanism, which is the main reason for the strength attainment of the geopolymer concrete, is like consists of three major steps. First is you can see here dissolution of silica and aluminum atoms by hydroxide ions from the raw materials. Then transportation of this, we call this as a precursor ions. Okay, this silica and aluminum ions and the hydroxyl OH minus ions. So this we call as precursor ions. So this first step is dissolution takes place. Then transportation of these precursors into monomers, like it's like chain like forming structures, like we can see here, siloxanate, disiloxanate, sialates, and all. Then finally setting of these monomers into polymeric structures. It's like SiO, ALO, it's like a chain type of structure will form and will condense, which will finally get as a hardened product as geopolymer concrete. So I'm not going deep into that mechanism. Okay, this is how it forms. Dissolution, then the presence of these hydroxyl ions, then reorientation will take place, and finally polymerization and hardening. And this we can see, this is the final product. These are the individual components, and these all will gel together to form a final product like sodium polysialate disiloxo. Yeah, this is the chemistry involved. The chemical mechanism can be interpreted in based on these steps. You can see first alkylation and formation of tetravalent aluminum in the side group sialate. Generally, silica aluminum is a trivalent, generally forms trivalent bonds, but in the presence of this sodium hydroxide and sodium silicate, it it forms like tetravalent bond. That's why we are having SiOl for this. You can see here. But you know this why this negative symbol here, because AL is a trivalent, but here the bond formation is having tetravalent bond forming taking place. So because of that, there is negative charge attached to aluminum. So now to balance this negative charge, we need a positive charge. So that will be given by the sodium hydroxide that we are giving as a alkaline activator in our mix, like during our mix procedure. And after this alkaline dissolution starts with the attachment of the base OH to the silicon atoms and sodium hydroxide to the aluminum atom. So cleavage of siloxane oxygen, that is SiO Si, through transfer of the electron from Si to oxygen, formation of intermediate silanol SiOH and basic siloxane will take place. Then further formation of silanol groups and isolation of orthosialate molecule. This is orthosialate molecule. Then reaction of basic siloxane means SiO with sodium and formation of sodium oxide and like silica oxide and sodium terminal bond. You can see here. Finally, condensation takes place between these orthosialate molecules, reactive SiONA groups, and aluminum hydroxyl leads to the creation of cyclotrisialate structure, this one, and followed by polycondensation into sodium polysialate nepheline framework. So this is the chemistry involved in the geopolymer. Yeah, this is the final further condensation to form finally a chain life structure. You can see here. Condensation between disiloxanate orthosialate molecules reacting SiO aluminum hydroxyl and formation of orthosialate disiloxo cyclic structure. So yeah, this most of you people know major difference between OPC and geopolymer. Only thing is here this hardening process is different here. Here even the strength giving components. Here main reaction is hydration reaction. Here the main reaction is geopolymerization. In the normal concrete, we generally get CHS gel, calcium silicate hydrate or calcium aluminum hydrate, and AFT and AFM. And for similar to ordinary concrete, what we generally target is the concrete strength, modulus of rupture, or you can say flexure strength, or and most important thing, the elastic modulus of concrete. Here also, only difference is there we are using cement and water. Here we are using industrial waste, which is rich in silicates and aluminates. And in place of water, we are using sodium hydroxide and sodium silicate, which I have tried with various combinations like lithium oxide, like sodium hydroxide, uh, calcium hydroxide. So all different second group elements I tried, but uh, finally what I found is of all these combinations, sodium hydroxide and sodium silicate will give the best results and best polymerization. So I did my like further work on by using sodium hydroxide and sodium silicate, and finally I got a concrete which resembles not ordinary concrete, even the strength wise also, like what we generally will be getting for a corresponding water to cement ratio, will be getting some strength. So the similar way also I got, even in fact I got little more than normal concrete for the same water to cement ratio. Here water to cement ratio is replaced with aluminum AS2, sorry, uh, binder solids to AAS, means aluminum activates like silicates. Okay. Yeah. So this I don't want to discuss more on the gap onto. Yeah. So this current research is like developing job using fly ash alone, what I told us earlier. 100% in fly ash and GGBS. So 70% fly ash and 30% GGBS. Then fly ash, GGBS and red mud. So 50% is the fly ash, 30% is GGBS and 20% is red mud. So what I observed with the addition of GGBS is we can avoid the heat curing. Otherwise, with fly ash alone, we need at least 70 degrees centigrade like heat curing for at least for 24 hours. Not for at least we can say it's optimum is 24 hours. Generally, so beyond that, it's not much. It's not adding much to the strength. So we can optimize to 24 hours at 70 degrees centigrade. So if we are going with fly ash alone, means it takes so much time, to activate and so much time to harden. So it's a better option is to go with uh, like uh, going for heat curing, or we can say we call it as oven curing if you are doing for smaller scale. And yeah, and I'm going to explain the step-by-step procedure for developing the mixed design. And then how we are optimizing the sodium hydroxide molarity and sodium silicate to sodium hydroxide ratio or the curing type and optimum contents of all this, the background to for finalizing the percentage of various percentage of industrial waste used in the study. So why I use it 50, 30, 20. So that is the background to that. Yeah. So, so there are so many factors influencing GPC. So some of the major I have noted here. So one is alkaline activator type, sodium hydroxide molarity, silicate to hydroxide ratio, and sodium silicate modulus, that is Na2O SiO2 ratio, like the amount of SiO2 and Na2 present in the sodium silicate solution. Then what type of curing you going for, and what the temperature you are applying when we are going for oven curing or heat curing, and what are the optimum amount of curing time. Then, and one more important thing is mixing sequence also very important. Okay, generally if you mix sodium hydroxide first and later if you mix sodium silicate, uh, the setting time will be faster. So it's better to go like first mix the sodium silicate and then addition of sodium hydroxide will be the better option, so that we can increase the setting times. Then activator solution to binder solids ratio, like what water to cement ratio. Here activator solution to binder solids ratio. Then ratio of silica to aluminum in the geomer system. Then binder metal composition. So this ratio of silica to aluminum plays a major role. So some materials will be having like more than 90% of silica, very like 4 to 5% of aluminum oxide. In that case, it's very difficult to attain to get the even to get geopolymerization process to go smoothly. So there is certain ratio is there. If we are in that ratio only, we are able to achieve good like you can say strength or other properties. Yeah. So this gives you an idea about the influence of various oxides on the final strength of, like you can say 28-day strength or 7-day strength of the geopolymer concrete. You can see here most this is the these are the points based on the like more than 35 to 40 like results research papers taken the data. Based on the data, what I found is the optimum composition that the waste should have to give you the better results is silica oxide between 45 to 55%, aluminum oxide between 22 to 28%, and calcium oxide and iron oxide together should be less than 20%. Then only you will be getting good geopolymer concrete strength. So I have a paper on this also. We can see like influence of iron oxide on the strength properties of geopolymer concrete. So we can see that there are so many citations also, almost can see more than 200, near about 200 you can say. That many citations are there on that influence of iron oxides. Yeah, you can see here effect of oxide composition on the 7-day country strength and 28-day country strength. You can see here with red mud alone, very less. With fly ash alone, this much. With high calcium, this much. With GGBS alone, this much. Okay. And you can see here in the combination, if you see. So these are all like based on the presence of calculating the amount of oxides present in each waste material or industrial binder material. So if you see here, so you'll be getting good strength when the range in this range only. And so this is general procedure. So I will not go through deep. So the optimum ratio is generally it varies with the type of binder material you are using, with the presence of the like silica oxide composition, aluminum oxide, and calcium. This may vary with person to person, material to material. So that's why you should not blindly go with these ratios. Many people will, many research papers will say uh, follow this molarity and follow this ratio. Should not go like that. You have to do at least trial test, not on a large scale. At least you do on the mortar, small mortar cubes, at least for 7 days and 28 days for each ratio by using the material you are using. So that depending on the material you are using, this may vary. So both you have to try. So at least fix one molarity, then try which one is the maximum optimum we are getting. Then you instead of doing everything repeatedly 8 and 1, 10 and 1, 14 and 1, 16 and 1, it is better to optimum one parameter. Like I'm optimized one parameter. Like I found out the optimum ratio, then I fixed that and I tried with the different molarity. So this may vary to each and every person, and not the person, we can say each and every the type of material they are using. So it is better to do this type of test. Maybe it only takes 1 month, because 28 days is the maximum you can target. So by doing this, we can attain the better results. Okay, because we already initially we finalized the optimum content, so we will get the better results in the, like you can say, if we go for concrete also. This is suggested to do for the mortar only, which is simple to do. Okay, yeah. So the reason behind this increasing NaOH molarity is found to increase the dissolution of silica and aluminates. However, excess sodium ions inhibits the geopolymerase. It hardens. Even molarity is more. If I increase the molarity also, that will affect the hardening process also. Even geopolymerase, there will be more number of sodium ions, and you will see sometimes. Most of the times you can see with sodium fly ash and GGBS combination geopolymer concretes, you see white layer formation because of this excess amount of this sodium present in that. And also it will affect your, yeah, I observed many people reporting RCPT results for geopolymer. But generally geopolymer, for geopolymer concrete, this RCPT will not work. We can see because of the sodium, we generally use sodium dissolution, means in RCPT we generally use what, sodium chloride in one side. Okay, so there are again sodium ions will dissolute, and it will be like moving from higher zone to lower zone. Again, that is actual process. But here sodium hydroxide is already there, so already excess amount of sodium are also. So because of that reason, so RCPT test will not work on geopolymer. Yeah, this is the for finalizing the optimum. We can say like fly ash and red mud combination, fly ash and GGBS combination. Yeah, actually, in the starting I told I tried with fly ash alone, fly ash and GGBS, fly ash, GGBS and red mud. Before that, I also tried fly ash and red mud, but with the addition of red mud, if you are, for suppose you are taking 100% fly ash, suppose I am getting some X amount of country strength. If I'm adding red mud 5%, 10%, 15% by keeping other things constant, uh, I observed like drastic reduce in the reduction in the strength properties. So that means we cannot use these two combinations because in red mud we don't have, at least in GGBS we have reasonable amount of calcium oxide. So because of that, instead of, in addition to geopolymerization, we are also having CHS gel and cash and CHS both. Cash also is forming CASH. So that is giving strength to fly ash and GGBS. But whereas in fly ash and red mud, in red mud mostly it is aluminum and iron oxide. So that will not contribute much to the strength of the geopolymer concrete. So because of the reason with the addition of red mud to fly ash, so I noticed decrease in the strength. So we can discard this combination. So we cannot go with this combination of fly ash and red mud for at least for geopolymer concrete, for developing geopolymer concrete. Okay. So next is like this is the most of the like it's even you can see many people are even using practically also this combination fly ash and GGBS even for roads, even for airport and all. In some places they use this combination. So here also I tried with 90-20. Even if you add, you keep on increasing the GGBS content, our strength will be increasing. But what we can we can notice is that with the increase in the GGBS content, there is a like problem of faster setting. So in order to have reasonable amount of setting times, means we should restrict the GGBS to 30% only. In fact, even if you can reduce 20% also, it will be good because of this GGBS, the content, more amount of GGBS content, the setting is taking place even sometimes before 1 hour also. If you add so much of like plasticizer, still it is not stopping that this setting. So it's better optimum here in this study. I consider is 70% fly ash and 30% GGBS. And if you see, on one advantage with this fly ash GGBS combination is, so I tried casting and curing cubes both in ambient curing condition and in elevated curing conditions like 70 degrees centigrade, lot what we generally use for fly ash alone geopolymer concrete. So I have not even noticed 1 to 2% variation also. Almost we can say less than 1% difference you can observe between the strengths for ambient curing condition and for elevated curing condition for 24 hours. So so you can discard this like elevated curing if you go with fly ash and GGBS. And yeah, so the red mud with the fly ash is not worked because I observed decrease in the strength. But it create wonder with the GGBS combination, fly ash and GGBS, not by uh, participating in the reaction, by filling the pores because this red mud particles are finer than this GGBS. Maybe initially we may not get finer, but we have to grind. You will get into like use blocks type of you can say red mud. I have shown a starting slide. It will not like powder is form. We have to grind it and make it powder. If you powder it, that will be finer than this you can say GGBS. So because of this fineness, this has entered into the pores found during this geopolymerization. Whatever the pores are there, that is filled uh, by the red mud powder. So because of this, I observed uh, if you compare to like fly ash GGBS combination at certain ratio, I observed 20% more when I used 50% plus 30% plus 20% red mud. 50% fly ash plus 30% GGBS plus 20% red mud. So I got up to 73 MPa for the ratio of 0.4, that is binder solids to AS ratio. Sorry, AS to BS ratio. No, I'm talking in the reverse way. So aluminum silicate to binder solids ratio of 0.4. If we compare with fly ash and GGBS of 70-30, then fly ash, GGBS and red mud of 50-30-20 combination, I notice like 73 MPa, which is more than 20% higher than what I attained for fly ash GGBS alone. And but we cannot go beyond that 20%, because I already told in the reaction it is not participating. Only it will act as a filler only. So this is the procedure. This all I think most of you people know. 24 hours oven curing if we are using only fly ash, or if we are using fly ash or GGBS. If we are adding GGBS, then there is no need of any oven curing. And yeah, these are the after developing, I studied the phase mechanical durability and microstructure properties. So these are you can see how fine the red mud is, but earlier it was not like that. So after grinding it, so I got this, and this fly ash and red mud. And actually this research I have done is sponsored by NALCO, which is in Odisha. And this is commercially I have brought from the chemical factory. And this is a super plastic naphthalene based super plastic. Even I tried with different types of super plasticizer, no one was working. So naphthalene based super plastic is the only option if and when are going for geopolymer. I don't know that nowadays what type of super plasticizer are there in the market, but during that time this naphthalene was the only option for me. Even I tried with PC based, but that is even retarding the strength. Yeah, here for the C1 analysis means for the aggregate composition, I used DIN data, DIN curves. Okay, DIN combined grading, DIN B curve I used, which resembles our normal concrete. Generally, there are DIN A, DIN B curves are there. DIN A we generally use for self-compacting concrete, and this is similar to the properties are similar to I say fresh properties, not the reaction properties. The fresh properties are similar to normal concrete, so I adopted a DIN-B. And generally, the DIN-B uses combined grading, not like our Indian code. We generally separate out the fine aggregate and coarse aggregate. But here it's combined grading. It consists of both fine as well as coarse aggregate. Here these are the various sizes like fine aggregate less than 4.75, and I use three different types of different zones of aggregates like 20 passing. All these are passing only, 12.5 passing and 6.3 passing. And the solution is sodium hydroxide. I already told in the previous show it is slide. It's 14 molarity, and the ratio between these two is 1.5. And these are the oxide composition. If we see there, I told you already, like when the silica oxide is 55 to 65, we will get good results, and if it is 25 to 35, so you can see here. So the material I use, it contains the oxide composition in that range only, in the top range only. And you can see here why this red mud is not giving a good strength properties, because it contains a very less amount of silica. So if you add this, it will further reduce the amount of silica present in the total binder material. Even though it is not disturbing the aluminum, but main thing is it is that Si to Al ratio is reducing with the addition of red mud. So this we are reducing this and we are increasing this. So because of that, the ratio is reducing. So because of that reason only, we are not getting good results when we are increasing the red mud content. Okay, I don't want to discuss about the drawbacks of others. Yeah. So the mixed design procedure I followed here is based on the absolute value method. Then even we also do for all our mixed designs. We generally use this absolute value method only by considering the specific gravity of the material used. So that means we are so you are using the volume here because we are considering specific gravity means so you are using volume. Then European standards, the Dean curves, and have fixed the alkaline activated solution to 200 kg per meter cube because to get the required workability minimum required based on the preliminary study what I found is like 200 kg is the minimum requirement to attain the required workability. If you increase, the cost will increase. If you decrease, the workability will decrease. So the optimum I found is 200 kg, and I kept this as a fixed for every ratio, even zero point 0.4, 0.5, 0.6, 0.7, 0.8. I did for like water to cement ratio here. Here I did for AAS to BS, means alkali activated solution to binder solid ratio from zero point 0.4 to zero point 0.8. For every ratio, I kept this AAS content 200 as fixed. So only variation will be binder solids. Binder solids will be more, okay, with the decrease in the decrease in the this ratio. And yeah, AS to BS ratio is 0.4 to 0.8. So first thing is fixing the total alkali activator content, then fixing the NaOH molarity. So this step has to be followed by everyone, means whoever uh, like developing geopolymer concrete, because the material will be different from place to place, and if we are using different material, not only this fly ash GGBS, this is valid to everyone. Any material which is which contains a good amount of silicates and aluminates, and if is calcium also is there, that will even help also uh, for the formation of cast, which again gives very good strength. And okay, this procedure is this you can read this procedure to any type of geopolymer. Only thing is these two steps you have to do preliminary study, fix the molarity and fix the ratio. Then this total AS also may change or may not change depending on the on your material used. So these two steps everyone has to do. Even if the same procedure I'm doing in the different location, means again like what we generally do for the like mixed design normal concrete also we generally do test the aggregate, what are the materials we are using. Likewise, we have to consider these two tests as a common test for the geopolymer concrete, like fixing the total AS requirement and fixing the molarity and sodium silicate to sodium hydroxide. Should not blindly follow some research has told this is the optimum. That may be optimum for the material used by them. So it varies. So this too is not that difficult. It takes hardly 1 month to find out the optimum values. So first we have to find out these optimum values, then select AS to BS ratio or target just by mimicking AS tends to water to cement ratio. You all, everyone knows that. So I will show that here. Mm, I'll go later. Okay. Yeah. So strength will be more when the water to cement ratio is less. So similar way here also, strength will be more when the AS to BS ratio is less. Then next step is we have to proportion the aggregate. Again, this also we have to follow DIN B. We have to suppose you have taken some X amount of fine aggregate, some Y amount of Z like 6.3 mm passed aggregate, some Z amount of 12.5 mm passing aggregate, and some W amount of 20 mm passing aggregate. So you already make an Excel for following the like DIN curves, DIN you can say the codes. I given give the reference code number also here 1045. Okay. So you can have an Excel and you play with the first you have to do the aggregate analysis for each ratio passing, like 6.3 passing, 12.5. Separately you have to do uh, uh, this analysis, CV analysis, then have a separate graph for that, Excel for that. Then you have to adjust the, like 30% is 20 mm passing, 20%, I'm just talking about example, 20% 12.5 mm passing, 10% 6.3 mm passing, 40% is fine aggregate. Then you have to see whether our cover is matching with the DIN B or not. So to match the DIN B, you have to adjust, increase 20 mm or decrease 20 mm, increase 12.5 mm or decrease 12.5 mm. So you have to play with that to match the aggregate proportioning to DIN B grading curve. So likewise, finally you will attain some, okay, 30% is this much this 20 mm passing, 25% is 12.5 mm passing, some maybe 15% is 6.3 mm passing, and 40% is fine aggregate. Yeah, maybe at one point you will get that curve will match to DIN B. So where you got match, where you at what point your curve matched to your DIN B curve, there the corresponding ratios you have to consider for the aggregates. Then we already fixed that proportion. Now determining binder solids content to various AS to BS ratio. So already AS is fixed to 200. Suppose uh, you are starting with 0.4, means the binder solids will be 500. So AS is 0.4 by BS is equal to 200. So binder solids is equal to 200 by 0.4. You will be getting about 500 kgs is the, so this is per meter cube. This all the mixed agent is per meter cube of concrete, which we generally do for any mixed agent. Then determining the individual alkaline activator contents. Yeah. So like so you already fixed AS, then already you know the ratio between sodium silicate and sodium hydroxide, and you know the total AS. So you already know the ratio and you know already total AS content. Then you can suppose in my case I got 1.5 and I'm using 200 as the fixed activator solution content. Now what will be my sodium hydroxide? Sodium hydroxide will be say 80 kg and sodium silicate will be 120 kg. So that I will be getting 1.5 ratio. So 120 by 80, I'm getting 1.5. So like that I will be, so first I fix AS, then I determine binder solids, and I individually find out the each alkaline activator content. Then by considering the mix proportioning for 1 meter cube, and we generally deduct 2%, what we usually do for normal concrete. Here also 2% for air entry and air content. So for 0.98 meter cube, so we are calculating the total volume, and we already know the binder solids content how much, and I already know the specific gravity of each material. And it's usual that for any mixed region we have to find out the specific gravity. You have to do the specific gravity test for every material we are using for the mixed region. So likewise we have to do for binder solids like fly ash. We are using fly ash. If you are using fly ash, GGBS and redmond. So for all the binder solids, whatever you are using, you have to determine the specific gravity. Then you have to determine the specific gravity for sodium hydroxide. Then you have to determine the specific gravity for the sodium silicate. Likewise, and then so initially we already determined to match that DIN curve. I'm going there. Yeah. To match this curve, how much percentage of 20 mm passing I used, how much 12 percentage of 12.5 mm I used, how much percentage of 6.3 mm I used, I already know. To match this, I already, after doing the CV analysis, after doing this combined grading, okay, uh, I determined how much percentage this, how much percentage this, how much percentage this. So in my case, so what, this may again vary with person to person, region to region, not person to person. One location to other location, it may vary. So say I got A percent, B percent, C percent, D percent. So to determine the weight of aggregate passing this much, so how much percentage of 4.75 passing I consider into volume, this VTCA, total aggregate volume, okay, into specific gravity of this 4.75 into 1000. So we will be getting in terms of kg the weight of 4.7 passing aggregate, likewise for 6.3 mm, 12.5 mm and 20 mm. Then once you get all this, and you have to do the mixing, proper mixing and the sequential mixing, what I told, like first mix the dry material, then mix add the sodium silicate, then add the sodium hydroxide. So this is this mixed design for various combinations. Fly ash alone 0.4, 0.5, 0.6, 0.7, 0.8. This 0.4, this is ratio alkali activator content to binder solids. Okay. So similarly for fly ash and GGBS. So fly ash 70%, 30% GGBS. Here fly ash 100%. Here fly ash 50%, GGBS 30%, red mud 20%. So for all these 5 ratios, so 0.4 to 0.8, here 0.4 to 0.8. So this is the fly ash. This total will not change. 500, 400, 333, 286, 250. You can see here. Weight will not change, but volume will change. That we can see here. Even the total weight is same, but aggregate also we have used like different, maybe same percentage, like 20 passing, example A%, B%, C%, D%. This remains same for all the makes, yes, but can observe here the variation in the weight of the aggregates used. That is because we are using absolute volume method. Here we are replacing fly ash with GGBS. Okay, so which I found is little coarser than fly ash in my case. Okay, so that's why the volume is changed here. And if we see a fly ash, GGBS and red mud, so red mud is more like specific gravity wise, because iron content is more, obviously the specific gravity will be more. So you can see, you can observe here there is more amount of this aggregate requirement, because the red mud is occupying less volume, but it is acting as a filler only. Because of that only it is giving, but volume wise if we see, uh, it occupies more. If you see absolute volume method, strength is a later stage, but initial stage is volume is most important. So volume wise it is occupying, for the same weight it will occupy more volume, sorry, less volume. Sorry, 1 minute. Yeah, this is the mixed design. And yeah, for lower ratios we don't need any super plasticizers. It will work with the, because this is 0.6, 0.7, 0.8 means the solid contents are less. It's hardly like 230, 333, 286, 250s, and we are using 200 kg liters of this one, not liters, kgs of sodium hydroxide and sodium silicate. So we don't need, for higher ratios we don't need any plasticizer, but for lower ratios we need this much. You can see here we need very high amount of sodium super plasticizer, because of this GGBS will have huge effect on the like setting times and all. So you need more, because during even setting time also it will start reacting. Yeah. So these are the tests conducted, like complete strength. All I done is 100 by 100 cubes only, up to 56 days. 3, 7, 14, 28, and 56. Split tensile, flexural, elastic modulus, rebound armor, ultrasonic pulse velocity, water absorption, sorptivity, water penetration, sulfate attack, acid attack, corrosion properties, pH or alkalinity, carbonation, chloride ion content, surface resistivity, off cell potential, corrosion rate, then microstructure, we see SEM and EDS analysis, XRD, FTIR, and TGA. So gravimetric analysis, thermogravimetric analysis. And this is the fresh properties. So this is the convection factor for fly ash alone. So compared to others, fly ash, the reaction will be very slow. So until we put in the oven, it will not fasten the reaction. So you can see more workability for fly ash alone, and it is reduced with fly ash and GGBS. When slump also same thing can be observed. And these are the, you can see here how sticky these are, but there is no true collapse type of structure. Only we can only observe collapse in like when we go with 0.8 or 0.7 for fly ash alone. And if you go with red mud and GGBS, it will be like sticky, even though it gives good workability with increase in the AS to BS ratio. Here we can see the mechanical properties. If you see the complete strength, this symbols 0.4, 0.5, 0.6, 0.7, 0.8. So as usual, with the increase in the ratio, our strength will decrease. So we can see here the maximum strength is for 28 days. We can see about 48, 47 to 48 with fly ash alone. If we see with fly ash and GGBS combinations, it is about 66, 67. And if we see, this is I'm talking about only for the maximum one, that is for the lower ratio 0.4. And if you see for fly ash, GGBS and red mud combination, which is about 73, 72, 70. So main thing for the main reaction product in the fly ash base is NaSH, sodium aluminosilicate hydrate. Okay, increase in the liquid content inhibits the geopolymerization. That is the reason. So with the increase in the ratio, and it is inhibiting the geopolymerization, which is usually this fly ash based GPS is usually depends on the geopolymerization only, mainly on the formation of NaSH. So that will inhibit the formation of NaSH. That's why with the increase in the ratio, we are getting like the strength is constantly reducing. Then why we got more strength with addition of GGBS is, in addition to NaSH, we are also having cash and CHS. CHS is we generally see in cement also, but in addition to this, we will be having NaSH and cash, which is giving strength to our concrete. And red mud, even though contains low aluminosilicate content, act as a filler material and enhances the properties of GPC. But this is not. This is only I observed only like good amount of increase in strength for higher ratios only 0.4 and 0.5, because with the addition of more solution, what is happening, it is not like there is no scope for the red mud to act as a filler, because this solution is occupying all the place, and there is no scope for this red mud to fill those places and enhance the strength. So that is the reason only for we can say lean mix. I cannot say lean mix. Like less workable mix only, we can observe a good amount of strength increase compared to the other like fly ash, GGBS and fly ash alone combinations. Same way you can, yeah, this you can see this is the strength to water to cement ratio as per ACA code. This is, so you can see here, flash based alone. These are my 5 points: 0.4, 0.5, 0.6, 0.7, 0.8. And I developed a curve which the R square value of 0.986. So you can, it's a good relation is there. So you can consider this. So you can consider this equation. So to get the 28-day country strength, 12.324 times AS to BS ratio to the power minus 1.359. So So directly want to jump on to the mixing the concrete means, so you can directly follow this. Suppose if the properties of your like binder solids are similar to what I have shown here, then you can directly jump on to this equation. Like suppose you are targeting, say, like 40, maybe you are targeting 40. What is the corresponding ratio? 0.5 to something. So directly you can start your like mix proportioning by considering AS to BS ratio as 0.52. So you already know the ratio, you already know AS, then you can find out the binder solids. So you already know the specific gravity of the materials used and all. So likewise, you can within minutes you can calculate the composition of various materials required for your targeted strength. So likewise, you can see here, uh, you can observe very good amount of increase in this strength compared to fly ash alone. So that's why even the ratio, the curves also, the distance is far away compared to fly ash alone. And here at the lower ratios, the curve is moving away, and for higher ratios, even though it is still higher than the normal, uh, like for normal concrete, what we generally get for this ratio, we are getting more than that. But for lower ratios, it is more or less we are reaching the strength what we generally achieve for the normal concrete for the similar ratios. So this is the different curves we have to use, like to strength to water cement ratio. You are also, you can use, you are using only fly ash, you can directly use this. In a similar way, the trend is similar. So I don't want to give focus much onto this, because there is no, like, even though maybe little bit of variation will be there, but the trend is remains same. Here is perfect curve, we can see here perfect improvement. Here there is not perfectly uh, like increasing and decreasing it, but more or less the trend is like with the age it's increasing, and with the ratio it is decreasing. So that we can observe the trend is similar to the that of compressive strength. But tensile strength is slightly lower than the normal concrete because of the brittleness of, so compared to CHS gel, Nash gel is brittle in nature. So because of the brittleness, so the tensile strength, if we compare, so you cannot directly take, okay, roughly we generally take 10% of the compressive strength will be my split tensile strength, but it will not, we cannot achieve that here in geopolymer concrete, because that is not valid here. Even that flexure strength also, where we generally use 0.7 root FCK. If you use the same empirical equation, it is not, it will not suit to geopolymer concrete. You will get lesser values, because the liquid content in the mix and age of curing seems to have an influence. And elastic modulus also, obviously it will be lower, because your flexure and tensile properties also uh, not as per similar to normal concrete. With means when we compare with country strength. So here also you can see elastic modulus. You may not have 5000 root FCK. Will not, that empirical equation may not be, means that's for cross check only. Uh, may not be valid for the geopolymer concrete, because it will exhibit lesser elastic modulus because of the brittle nature of the geopolymer structure. And I found only for lower AS to BS ratio concretes, that is like 5.4. I noticed like the concrete quality is excellent. From the, based on this ultrasonic pulse velocity, I found that it's more than 4.5, and we can observe here for 0.4 ratio only for GGBS and GGBS red mud combination, fly ash GGBS red mud combination only, it is showing concrete. But overall we can say, for except fly ash, GGBS and Redmus per 0.8 ratio, all are showing fair to excellent like quality concrete. So you can see less pores. In that you can see like that. Then when I notice the rebound hammer results, I notice almost similar type of results because it gives only this surface hardness. So surface hardness of this geopolymer resembles that of the normal concrete. So this is because there is no empirical formula. So none of the empirical equations available for normal concrete seems to be valid for GPC. So we should have a separate, should do more research, more cubes to be casted, more materials to be tested, and before arriving at the empirical equation for geopolymer. With my 5 mixtures, I cannot. If I give also, it's not correct. Even though I tried, but that's not the correct way because with five mixes, we cannot give an empirical equation. Even this that compressive strength one also, you should do more number of you can say test. Then only we can do this better, like develop better mixed region curve, strength versus A to BS curve. So, so I prefer like there is more work to be done on this geopan concrete with respect to the empirical equation point of view. If we say like this 0.7 root FCK, 5000 root FCK for elastic modulus, then roughly 10% of compressive strength for split tensile is not valid. So there should be more research to be done on this, and they need to develop. You can see here. These are the various curves relationship, uh, and this is a curves from different countries: Australian, British, Eurocode, Indian, CEB, ACI. So for different codes, it's differently they are showing. But all other codes they don't use FCK. They generally use FC dash. They generally use cylindrical strength. Even in my when I do the design also, mostly it will be FC dash only. Sorry, cylindrical compressive strength only. Only VIS code use FCK. So this is similarly for elastic modulus also. This various what different codes says the relation. This is actual value. Yeah. So this is what I actually got. These values, the probable values based on the various codes. If I use ASA 318, what should be this corresponding elastic modulus for the for so on so for suppose this is so my compressive strength is suppose 50 MPa. What should be the like elastic modulus as per Eurocode? Like I plotted like this for different country codes. These are this what should be the actual as per the empirical and what we actually got. You can see even not a single code is near to our value. So everywhere we are getting lower value than the empirical equation developed means provided by various countries. You can see only you can see flexure. It is some countries is above showing above value and some are showing, but no one is closer. So you can see only the British are. I can say Asia. They are just near also. Most of these are like so we cannot directly rely on the existing empirical equation. So that is what I want to say. And next is durability. So softivity. So softivity is obviously with the increase in the AS to BS ratio, the softivity will be like more. It will absorb more water, And yeah, so I have done subactivity test as per ASTM C1585, and this is the trend you can observe here. The increase in subactivity indicates presence of more capillary pores in the matrix. So that is the obvious reason. So more subactivity means more it is sucking that water because of the continuity of pores. This subactivity mainly thing is continuity. The more the continuous pores, more will be the subactivity. So if there is dense concrete and there is break in the continuity or there is discontinuity of pores, even though amount of pores may be same, maybe voids, if you measure the voids and same amount of voids in one cube may give more subactivity. Okay, same amount of voids in other will give the less subactivity. That purely depends on the connectivity of the pores. Okay, so yeah, you can see that with the increasing the AS to BS ratio, obviously the pores will be more. So the subactivity also is showing the same trend, same thing. And one more thing, ISTM says if it is less than 0.98, we cannot bring any correlation between compressive strength and subactivity. So that's why I have not done any correlation. Then, yeah, then find out the quality of the concrete based on the water absorption and penetration depth. So when the 30 meter water absorption is less than 3 is means low rating, between 3 to 5 is 5 average rating, above 5 is high rating. So concrete quality you can say is poor when the absorption percentage is more. So you can observe this. All are good except this at the ratio of 0.8. And there is no such type of criteria. This criteria is valid only for 30 minutes absorption. And this is water penetration depth. We can see the water penetration is that means we need more cover when are using the lower strength concrete. That is when are using zero point 0.7 and 0.8 ratio AS to BS ratio concretes. For this, we have to make sure, like be careful while providing the clear cover. So because the penetration is till this 26.5 means if you have 25 cover or 20 cover, then that will affect the corrosion. Yeah, this is except for point F, like 0.8 fly ash and fly ash GGBS and Redmond 0.8, all are showing good quality. Then correlation between, there is a good correlation between various parameters. We can say 99%, 99 R value 0.97, R value 0.96. So we can consider this correlation is we can consider it as a good correlation. So you can see the voids, final water absorption. If you have permeable voids and final water absorption, so it is giving a linear correlation. So that means with the increasing the permeable voids, the water absorption is increasing. And also if you compare with water absorption to water penetration depths, it is showing the same trend. With the increasing the water absorption means there is increase in the water penetration depth. And finally, subactivity and water penetration also has a correlation because more water penetrating means there is continuity of pores. That's why the water is able to penetrate to that far. So we can say that permeable voids influence the water absorption. So this linear relation indicates there is a good linear correlation between the like subactivity, water penetration, water absorption with the capillary pores. Yeah, then again, sorry. Yeah, so same, already covered that. Then resistance. So you can see here, these were tested for 20 weeks continuous. 1 week kept in like dry condition, 1 full week. Then 1 full week in 5% acid environment. I use 5% H2SO4. what I notice, you can see this is first day, and the only thing is this smoothness has gone. But if you see the weight loss, 2.15% is the maximum. Okay, that maximum is for the lower ratios. Like we can say AS to BS ratio is 0.8. I got we can say more loss. When AS to BS ratio is 0.4, it is intact. You can see the last one compared to these two. The surface is little okay. Even we can observe, even in all the three, all the specimen we can observe edges still there. Compared to this, maybe little worn out because loss has taken place. But for lower ratios, we can see 1.1% is you can say it's very less. Under similar exposure condition, the weight loss of normal context will be 10 to 15%. We can say the resistance to acid environment is very exceptional, not very good. We can say exceptional for this geopolymer concretes. Then sulfates also. You can say here weight gain is not that much. You can even ignore this. It's like minimum. That too, that is more when the ratio is more. Because of more porous, that will acquire that pores and whatever the sulfates and all we we made these cubes exposed to. So that will that may be the reason even the slight increase. But overall, if you see, this is starting only color changed, but you can see even same members only color only change, and there is not much you can say expansion, and little bit of weight gain is there. That is maybe due to formation of ettringate. If more formation of ettringate is there, means that will disintegrate the binder material from the uh, aggregate, and that will leads to loss of strength and loss of material. Okay, here that is not happening. It's very minimum. Because of this very minimum, it is absorbing that, and it is instead of reducing losing weight, we can notice increase in the strength. Sorry, increase in the weight, because it's not expanding uh, hugely, and it's in negligible expansion, and that sulfates are going into the whatever the small pores on the surface are there, that is giving little bit of weight gain. So overall, there is not much effect on the concrete. You can see maximum expansion is 0.03, and even after exposing to 15%, generally we don't get this much of exposure. Even worst condition also. Even when I exposed this to 15% to hasten the sulfate action, what happened? What I observed is very less amount of 0.03% and 0.04%, 0.04% only, which will come under highly sulfate resistant concrete. I think okay, time is there. Yeah. Then next is the alkalinity and carbonation studies. So you know that Na2O content and OH mass condensation increases with the AS to BS ratio. Because of that, the pH also will increase. Because of this hydroxyl ions presence, and then this content is increasing. So we can notice this. With the increase in the AS to BS ratio, even the pH value also increasing, because the alkalinity is increasing, and mainly because of the presence of the sodium oxide and hydroxyl ions. And if we notice, it is a good indication that it will be good. It will give good resistance to corrosion of steel, because all this everything is about 12. So nothing is below 12 pH. So everything is all geopower concretes having good alkalinity, so it will be good for even corrosion resistance also. And this is the carbonation studies. So we can see almost nil carbonation in fly ash alone based this one geopower concretes, because hardly we have 4 to 5% of calcium oxide in fly ash we are using. But whereas with like fly ash GGBS and fly ash GGBS red mud, you can notice like little bit of carbonation taken place compared to, you can say, only fly ash alone. You can see here, this is fly ash alone. Everything is, so there is no color means some reaction taken place. Color is indication means there is it's not reactive. And yeah, what I already told is because of low calcium content, fly ash alone is having very is affected, like carbonation wise is the least affected. Then chloride ion penetration, yeah, it's like obviously with increasing the porous nature of the concrete, this chloride ion penetration also will increase. We can notice this. And of all, like in every case, we can notice with increasing the AS to BS ratio, the chloride ion penetration also is increasing. And resistivity, they are showing very good resistivity, and this resistivity we can link to the porosity. High porous concretes are showing you can see here resistivity values, or resistivity is value less means we can see the porous nature. More porous means the value will be less. So this is low, moderate, high. Then offset potential, and the same like we can notice the same trend. Then corrosion rates. Corrosion is also with the increasing the AS to BS ratio. We can observe least affected is the having the concretes with low AS to BS ratio, and highly affected is the concretes with. But everything you can say maximum is nothing is abnormal. Everything is below intermediate, moderate, and we can say negligible also. Zone 1, you can say like for fly ash and fly ash GGBS, I noticed negligible corrosion. Then only I can notice intermediate, moderate to intermediate, when the ratio is like 0.6, 0.7 and 0.8. But if it is 0.5 or 0.4, 5.4, you can say whatever the ratio below 0.5, you will be having very low and negligible corrosion effect. This corrosion again depends on the permeation, as all you people know. This permeation usually influences the corrosion behavior. Relation, you can see surface resistivity. Higher the concrete strength, higher the surface resistivity. Even and lower will be the offset potential. It is vice versa. If more resistive means less, can the potential will be less. Then corrosion rates also you can see with increase in the strength means at low water to AS to BS ratio concrete, the corrosion rate will be less. Then I will quickly go to the SEM analysis. This you can see pores, shown more pores, and very we can see it's very clearly you can see the like crack type of structure here. Here, if you go on increasing the AS to BS ratio, this is because of the poor bonding, some unreacted particles. You can notice here, and you can see these pores. And this is the material, the spherical, and this is like irregular shape particles, and red mud is different particle shapes without any regular pattern. So at least we can have regular pattern for fly ash, but here with red mud we don't have any regular pattern. And the main thing, this is the Nash. You can see this type of structure. Then cache, you can see this is different. And you know, everyone knows, whoever knows about the normal concrete, how the CHS look like. So this you can observe what type of reactions happening with the fly ash alone. You can see here. Here you can see different reaction products happening, because by looking at the microstructure we can see here you can have all are similar only, all are of NaOH structure, like this type of structure. Okay, and yeah, so if we go on increasing the ratios, we can see a less amount of reaction products and more of unreacted particles, and more of porous nature. Then EDS analysis. So SA by AL ratio, elements by percentage. I can see SI to AL ratio, sodium to SA by AL ratio, and this is the individual materials, silica composition, silica element composition, aluminum, calcium, iron, sodium, this combination. Then 1 minute, the ratios between them in the material. Then when we add to like as a while mixing, we add fly ash and GGBS, fly ash and GGBS and red mud for various ratios. So this is what I noticed. Like this is increasing calcium to Si plus Al ratio is decreasing. So with the decrease in this ratio, there is I notice a decrease in the strength. When the Na by Si plus Al, the sodium content is increasing, means also that is affecting the geopolymerization. That's why there is a decrease in the strength. So initially, I told further increase in the molarity or further addition of more amount of sodium silicate and sodium hydroxide is like inhibiting the geopolymerization process. So this you can see notice here from the EDS analysis. With the addition of more amount of the presence of more amount of AAS, the ratio is increasing. The Na to SA plus L ratio is increasing. That is hindering the process. That's why we are getting less strength. So for high ratio of Ca, so more amount of Ca means we are getting other products like cash and CHS. Because of this, we are getting a good strength for even fly ash or fly ash GGBS or fly ash, even that may be very less amount of cash formation with fly ash alone, because my calcium is maximum is 1% only. So maybe you can ignore this, but still you can observe here with the decrease in the ratio that is affecting the strength. Again with the increase in the SA by to AL ratio, also more amount of aluminum also will hinder. So that's why here you can notice the same thing here. With the Ca by SFL decrease, we are observing decrease in the strength. Increase in the Si to L ratio, we are observing decrease in the strength, and also with the increase in the Na to ratio, we are observing that. So like this, so from this we can see that the influence of like the composition of the industrial waste, the binder solids plays a major role in each and every property of the concrete developed. So that's why we should not follow anyone's any like researchers uh, like mixed region blindly. So we have to do analysis on our own, like molarity may vary to each case to case, and your mixed region may vary to material. So first two steps we have to do um, compulsory. Then other steps can be repeated to any type of material. So this is about EDS. and you can see same thing. Then XRD, I don't want to go much more about into this. And the same you can observe here. I will give final statement. And finally, FTR and TGA. So Si silica oxide and SiOT band positioning characteristics of SiFO units formation in the chain structure of CH type gels. So more presence of this means better formation of this CHS type gel. And HOS bending vibration and OH bond indicate the presence of structural water. If this is more means you can say here Nash formation, high amount of formation taken place here, Nash. This is absorbed free water, then structural water associated with Nash gel, then dehydration of other. This is from TGA. So we can correlate TGA and FTIR with these bonds present for each and every, you can say, composition like AS to base ratio. You can notice this. CO bonds indicate the carbonation due to reaction between the free sodium hydroxide and CO2. Carbonation formation hinders the recreation of more reaction products. So more amount of CO bonds means it will hinder the creation of more reaction products. Increase in the intensity of absorption bands corresponding to SiOT, OH, and HOH bonds enhances the strength properties. If these three are more here, these bonds are more, then we can say that the strength properties also will be good. Is same for different different concretes. And TGA, and you can notice weight loss between weight loss between 105 to 300 degrees centigrade, which corresponds to the loss of structurally bound water associated with NaSH gel and cash gels. One of the reasons for this greater weight loss could be due to the loss of structurally bound water associated with NaSH gel and cash gel, NaSH and CHH gel. This observation is well agreement with the results reported by Nedeljovic, who have clearly reported that total mass loss in each sample is from interlayer and structurally bound water either in NaSH or cash gel within the temperature range of 105 to 400. The precise effects of weight loss on the strength characteristics cannot be quantified based on the TGA. So we can just notice uh, huge loss in this region means there is a formation of NaSH is very uh, huge loss means there is huge loss of water from the NaSH gel formation. Less water loss means less NaSH formation. More water loss means more NaSH formation is there. But we cannot directly correlate with TGA. We cannot specifically cannot say that because of this alone, because of the, more weight water loss. Okay, this is having more strength and this is having less strength. But precisely we cannot tell. But we can approximately we can say okay because of this reason we are noticing more loss of bound water, structurally bound water. And finally, what I want to conclude is first thing is oxide composition of the material we are using is important. Okay. Next is the molarity of the sodium hydroxide we are using. Then the sodium hydroxide to sodium silicate ratio we are using. Then the combination again varies with the material composition, with the oxide composition of the material we are using. Okay, then I can say that so for with increasing the S to BS ratio, obviously the strength is decreasing, and for every mix, for all the mixes, which is similar to normal concrete, then we can say we cannot correlate, we cannot use the empirical equations blindly what we have for normal concrete. So GPC we should have separate empirical equations to find out, to just without doing any experiment, we want to use the flexural strength properties, or we want to use the elastic modulus properties of geothermal concrete. We should have rigorous research on that, and there should be a separate like empirical equation for the geopolymer concrete. And finally, like durability wise, this is the best compared to normal concrete in like acid resistant point of view, alkalinity, pH point of view, corrosion point of view, but not all the for all the ratios. For like you can say up to 0.4, 0.5, 0.6, more or less we use that ratio only. We don't go 0.7, 0.8 generally for structural concrete. Maybe for non-structural purpose we can go for 0.8 also ratio, but more or less 0.4 to 0.6 is the generally used ratio. So for all this we can say this is the best compared to normal concrete. Yeah, that's all from me.
Thank you, sir.
Thank you, ma'am.
Thank you for an enlightening session, sir, on development of structural geopolymer concrete using various industrial waste. The session has deepened our understanding of innovative, eco-friendly alternatives in structural concrete. We are grateful for the time and effort you took to share your expertise and perspectives with us, sir. I'm sure the participants have gained valuable knowledge and inspiration from your session.
Thank you,
Now we
ma'am.
proceed to the interactive question and answer session.
Yeah. So yeah, I left in this research field some 2 years back. So you people maybe uh, might have done more research on geopolymer concrete than me. But however, whatever knowledge I have, I can share.
Participants can ask their questions in the chat box.
I think most of the people might have having more knowledge than me because
One
out
question.
of 10 people, 5 people will be doing geopolymer only. Even when I was guiding MTech people, most 50% will be any material change.
So one question, sir.
Yeah, tell me,
What
madam.
are the research opportunities in geopolymer concrete, sir?
So there is still scope for improving the workability. Workability is the major problem with geopolymer concrete. If workability we can able to achieve the workability by using some maybe by developing new superplasticizers. There is tremendous opportunities. Actually, every company is saying net zero carbon, net zero carbon. People going like green buildings, and only structure people can only save contribute to sustainability, but just by replacing cement with this waste materials. Only thing we can do is that, or by we can say replacing normal steel with other materials, natural materials or fibers, or by you can say reusing recycling the steel or recycling the aggregate. So this way only we can contribute the sustainability. But nowadays every company, every big company like Jacobs, WSP, Acom, these are the like we can say top 5 companies in the world regarding this uh, design or any infrastructure design and construction wise. I will not say construction, but mostly design wise. So they always prefer going for sustainable materials. So if we could able to provide a concrete, geopolymer concrete with better workability or better setting times, then everyone can replace cement with this cement based concrete with geopolymer concrete.
Sir,
That is
one
the
more
only.
question.
Yeah, yes, madam.
Sir, good
Sir,
evening,
what is
sir. Ma-
Yeah, yes, madam.
Sir, good evening, sir. This is
Good evening,
Seshi
madam.
Kumari.
Yes,
I am a
madam.
research scholar from Andhra University.
Yeah, madam.
Yeah, sir, just like when you are talking about geopolymer concrete, you have mentioned that elastic modulus is less. The practical values are less when we compare to all the empirical formulas, like all the codes, right?
Yeah, few codes
Sir,
it is matching, few codes it is,
yeah.
but those
But
codes are actually they use FC dash.
okay,
They
sir.
don't use FCK. FC dash is
Okay.
like you can say 80% of this one only.
FCK.
Yeah.
Yeah. So, sir, my doubt is like, like if the elastic modulus is below when we compare to all the empirical formulas, so then what can we like draw the conclusion? What conclusion we can give, sir, in that case?
So can say means I will only say that we need to do more like more tests and with we only with 4 or 5 like combination and with 4 and 5 also it's not correct way to even comparing also is not correct way, but even compared like just part of I want to just know how it is behaving, but we cannot do anything. We simply when we are using geopower concrete, we have to tell we have to we should have separate specifications in the code for geopower concrete also. Should
Sir, like,
provide. Yeah.
is it like only geopolymer concrete is give practical values are less, sir, when in your research when you are doing? Practical values of conventional concrete is matching with the empirical formulas, sir.
Yeah. Those will match only up to like 40, 50 MPa only. Those will match. Not for high strength. High strength is you obviously will get lower elastic modulus for high strength concrete. And
Okay,
even normal concrete also, even flexure
okay, sir.
strength, split tensile strength, or elastic modulus. All three will give you lesser values if you go for high strength concretes,
Okay, sir.
because there will not be any strain, much strain. If you observe, some students may be doing research on high strength concretes, maybe more than
Yeah.
100.
Yes.
When they do computer strength test, the sudden break you can notice. Huge
Okay.
sound will come, but for 30 40 we don't observe that much like huge sound, and crack also will be slowly propagating. Sudden
Yes.
breakage will not happen because of
Okay.
this is more brittle. High strength is brittle always.
Yes, sir. Yes, sir.
So
Yes,
brittle
sir.
means you will not get, definitely will not get elastic modulus,
Yes,
will
sir.
always be
Yes.
less.
Yes,
Yeah.
sir. Yes, sir.
Yeah.
Yes.
And someone
Sir,
asked that
one more thing.
One more
Sir,
durability.
one
question.
more thing.
Yeah.
Sir, like, so how, if we are getting the less values, how can we justify, sir? We can say that, like, we have to do
We
more
can
research on it. That's
justify,
it, sir?
only justification we can do is here the strength giving reaction products are different. Normal concrete is
Okay.
different and this is different. So these
Yes.
products are brittle in nature compared to CHS gel. Because
Okay.
of the region, we are getting lower like elastic modulus. So you should not follow like empirical equation given for the normal concrete. That we can defend in that way.
Okay. So the empirical formula, whatever we have in the codes, it's only applicable for conventional
Yes,
concrete.
yes.
So
That
that
too
may
up to
not be followed
certain
for
certain
GPC.
limit of like we can say, if you see Euro code, if you
Yes.
see ASA code, it's not a single. Uh, Not to Asia also they are given 4,700 root FC dash. If you see
Yes,
Euro
sir.
code, based
Yes,
on
sir.
the FC value, they are given different empirical equation for depending on the FC value. The lower FC value, they
Okay.
have different empirical equation. For higher FC value, they have different empirical equation. Only
Yes, sir.
we are following like 5,000 root FCK.
Yes, sir.
And ACA also is still following 4,700 root FC dash.
Okay, sir.
But others are just they are changing with the strength of the concrete.
Yes, sir.
And one ask durability properties. Yeah, actually 15% I used MGS4 because of that reason only. Because I cannot wait for 5 years in the doing PhD there. So what I did, I taken 15% of MGS4, which is impossible that any structure will in its lifetime will like expose it to. So that's why I taken a huge amount of 15% MgSO4 solution for doing the sulfate attack test. Even for acid also, what
Sir,
I
one
use it
more
that
question.
acid also I use very high amount of acid, which is in general will not any structure will not expose it to.
One more question, sir. What is the research gap in geopolymer concrete?
Yeah, first gap is there is setting times is a big problem. even I also hardly got, I think 140 minutes or 150 minutes. It's not, you should have plant there, directly mix there, place there. It's not possible practically. If we're having very less, uh, yes, someone is asking HCl and MGS for acids. Oh, I done research prior to using HDSO4. I from the research I found that of all acids, HDSO4 will have more acid effect on geopolymer concrete compared to others. Okay, so where I was? Sorry. Hello.
Hello, sir.
Yeah, madam.
I'm seeing questions, sir. Participants, if any questions, you can post in the chat box.
So there are plenty of opportunities in Japan, but everyone is just we are mostly doing replacing one material with other material, but we are not. I even can say all will not be having the facilities to do new research. Only we can do is mixed design, like acid attack, sulfide attack, water absorption, but we cannot do. Most of the people won't get the opportunity to analyze the material composition and try different plasticizers, how it is behaving. We cannot, we don't get that much. But people who are getting those opportunities better to concentrate more on increasing the setting times. That
Yes,
is the
sir.
only drawback.
Yes, sir.
Yes.
Thank you, sir. Thank you for your wonderful session, sir. On
Thank you,
behalf
madam.
of the organizing team and all participants, we extend our heartfelt thanks to you, sir, once again for this informative and thought-provoking presentation.
Thank you, madam.
Thank you, sir.
Thank you, madam. Now do, madam. Is there
Yes, sir.
anything else? Yeah. Thank you, madam.
Dear participants, with this we conclude today's Day 5 session of our AACTE ATAL Faculty Development Program. We sincerely thank our esteemed resource persons and all participants for their active involvement throughout the day. Participants are kindly requested to fill out the feedback form for today's sessions. Kind attention to all the participants. This is to inform you that tomorrow's schedule is as follows. Session 1 is on from 1:30 p.m. to 3 p.m. Session 2, 3 p.m. to 4:30 p.m. And session 3, 4:30 p.m. to 6 p.m. Valedictory starts from 6 p.m. and continues up to 6:30 p.m. Exam session is from 6:30 to 7 p.m. All participants are requested to attend the valedictory session without fail. Thank you. The ATAL FDP will resume tomorrow with day 6 sessions featuring more enriching lectures and discussions. Thank you all and have a wonderful evening.